Hi, can you hear me? Hello? Anybody, can you hear me? Any on the staff, can you hear me, please? Hello?
Yeah. Yeah.
Okay. So I see in the room there are many people. Do you know why they are not joining the Zoom? Or are they able to hear me? When I log into Gathered Town, I see around in that specific room around 20 people. But in the Zoom,
Sure.
I see only one. Can you go to that Gathered Town room and ask them to press X, join the Zoom?
Yeah, sure.
Hello, everyone. It's already 10 o'clock. Should I start? Anybody in the ES Week staff? What's the protocol?
Yeah. So maybe you could directly start. Yeah, the recording is going on.
Okay. All right. Thank you. Good morning, good afternoon, good evening, good night, wherever you are. So we have only 4 people in the 4 or 5 people in the tutorial. Let's make it as interactive as possible. Let's start with each of you introducing little bit your name, and at least put your full name in the list. Some of you are appearing as abbreviation. Can you edit your, go to the participants and then edit your name, please? Put your full name so that I can refer you correctly when I'm presenting. And also, can you start briefly talking about who you are, what do you do, and how much you know about hardware security or verification in general. So based on my list, so what's the name of ES Week staff? Can you replace your name so
Yeah.
that I
Hi. I'm Xuan Xie. So I'm in the University of Alberta. I'm a PhD student. I'm generally interested in verification and testing of cyber physical system.
thank you. So next in my on my list, it's someone appearing as LBAI. Go ahead, please. Okay. Next in my list is Chiachi Lin. Can you talk for a minute or two, please? All right. Next in my thing is Ashrafi.
Hi, Prabhat. Good morning. I'm Ashrafi. I work for Synopsys. I'm in Ottawa, Canada. I have a software cybersecurity background. I've been working on cybersecurity for almost a decade now, close to a decade. But I'm new to hardware security and hardware verification. So I'm really looking forward to get some basics and how we can bring cybersecurity verification to hardware. Thank you.
Thank you, Ashrafi. Next in my list is Praveen.
Hi, good morning. I am Praveen Srivastava. I am from IIIT Allahabad, India. I am a researcher over here. I am doing PhD, and I primarily work for the ensuring trust in the system at the software level, like software security. So I mainly focus on the runtime analysis of the program, and this hardware security and trust verification I am interested in to look further. So that's why I'm attending this talk. Thank you.
Okay, welcome. So in that particular room, I can see at least 2 more people, Siddharth Gupta and Miking San, Wen Chen, actually few more. Can whoever is in the ES Week staff, can you go in and tell those people to join the Zoom link, please?
Sure.
At least 4 more people or 5 more people are there. Can you have a look and tell them to come? Okay. All right, let me begin. And so I'm going to go slow, and since it's only 4 or 5 people, and we'll make it as interactive as possible. So when I'm presenting, please don't wait for the last minute. So I'm going to, as I talk, please stop and ask me. No need to put your text in the chat. Just keep talking. Keep asking me the question. And around 1.5 hours during presentation, I will pause so that you want to take few minutes of break. And then we'll conclude as usual by in 3 hours mark. So I am Prabhat Mishra. I'm a professor at University of Florida. And I have been at University of Florida almost 20 years. And I'm an IEEE fellow and an ACM distinguished scientist. So what we are going to talk today is about hardware security and trust verification. So if you know hardware security, you have idea of verification, it's going to be pleasant. But even if you don't know any of them, it's fine. I'll still cover very basics. I'll go very slow. But the key idea of this tutorial, since there are only 5-6 people in this room, the key idea is basically please interact, please ask questions. So what I'm going to cover today is basically 3 major aspects of what is hardware security. Do you see my slides in the full screen mode?
Yes.
Yes.
Okay, thank you. So what we are going to do is what is hardware security and why it's a big deal? Why are you even talking about it? So that's we are going to cover. Then we are going to talk about, most of us do simulation anyway, whether in software or hardware domain. What is the corresponding counterpart for security verification? How can I do simulation for security verification? What does it mean? And then I'll connect that with side channel analysis. What is simulation and side channel? Are they similar, friendly, unfriendly? So that's basically the scope. And finally, I'm going to talk about at least few scenarios of how we can do formal verification for different security objectives. Any of you have any questions on the outline or anything else you wanted to hear in the conversation that you don't see it here? I would be happy to accommodate and as I go along and not talk about some of the stuffs.
I have one thing. I have seen some some identification based on the hardware performance counters. So based on the hardware performance counters, we can identify some of the malwares which destroyed themselves or they move around here and there. So if you touch little bit on that side, like how I can utilize some technique for identification of those kind of malwares. So
Absolutely. So actually, I actively work in malware. We have a recent publication in IEEE transactions on computers, how you can use hardware performance counter, embedded trace buffer, and many other hardware features for malware detection. Intentionally, that's not in this presentation because technically speaking, malware detection or anything to do with that is not treated as a hardware attack. It's treated as a malicious software attack. But I'll be happy to talk and cover when I'm talking about HPC in a different context. I'll talk about it, specifically
yes.
Spectre meltdown kind of story. But offline or even after the tutorial, please feel free to reach me and I'll be happy to talk about it.
Sure, sir.
Anybody has, thank you, Praveen. Anybody else has any comments or questions on the scope?
The Ashrafi here, Prabhat. I think
I can see who is talking. Actually,
Okay,
you guys can turn your camera on. It's such a small audience. I'll feel comfortable unless you are not comfortable. That's fine.
yeah, sure. Once I finish my breakfast, I will start my camera. So I think I am very interested in assertion-based validation. So maybe if you can spend a little more time about the basics of that, that will be very helpful for me. Thank you.
Absolutely. Anybody else has any other comments? Okay, so I'll take care of that. So what is the scope of what we are trying to do here? The scope is when you talk about hardware security, we are talking about systems, specifically connected systems. So hardware security doesn't basically mean, oh, it's just the hardware processor. Sure, processor is talking to somebody. So it's a computation security, communication security, as well as storage security, if you look at that way. If you can further partition, it's a security at the device layer, security at the system layer, as well as security in the circuit/architecture or hardware layer. So today's tutorial is primarily focused on this. I have extensively worked on system layer as well as devices layer. Feel free to ask questions, but tutorial will primarily cover the hardware security in this layer and the verification issues related to that. So the best way to understand whether hardware security is an important problem is to go to this Mishra Corporation or NIST website where they basically enumerate all the common vulnerabilities known today. So this website was originally designed for software only story. cybersecurity side. Recently, they started putting in vulnerabilities and known attacks on hardware also. So I basically looked at the data and tried to kind of put them together. How do they look, that data? Now, of course, this diagram is obsolete as soon as I present it. The reason being, anytime there is a conference, whether it's a black hat, red hat, any of the conference where you kind of demonstrate an attack, that website gets updated, added. So in the upcoming ICCAD conference, we are showing an attack on AMD processor on load buffer attack, and immediately after the conference we can expect it would get an entry in that website. But no matter what it is, if I look at it, a significant portion on billion is a hardware plus software kind of vulnerability. And if I zoom into just that component, hardware plus software, we are looking at many of the attacks that you already kind of know, whether buffer overflow attack, that's also true in software domain, and then permission privileges attack, resource management, information leakage, crypto errors, code injection, and so many other. So basically, remember, these are the vulnerabilities, and some of these vulnerabilities have led to attacks. Some of them have led to many attacks. Some of them had gone to less attack. But if I look at just, let's say, buffer errors, which is a bigger chunk, I wanted to say something here. So this buffer overflow has been known for decades. And people actually know what it is. It's a \0 problem. And by bypassing that, you are able to write in somebody's area. You are able to read from somebody else's area. You are reading my program, I'm reading your program. Your program is reading my data, and so on and so forth. If we are running the programs in the same system, same server, same cloud. Now, the question is, if we already know what's buffer overflow problem, if we already know how to fix it, why are we talking about it? The reason we are talking about it, here is a plot. This is the only data publicly available. And that plot basically shows, although we know more than 20 years, the number of buffer overflow attacks actually increasing. It's not actually going down or just vanished. So nobody is doing the primitive attack. People are mixing with some complex scenarios. And as I go along, I will slowly introduce a lot of such complex scenarios. And then you kind of get a feeling, oh, that makes sense. Even known problems, known solution, under certain permutation combination, suddenly it becomes too much. And so that's basically one thing happening, is that there are so many errors we need to, or vulnerabilities we need to handle. And then there is some stuff that are against us as in the people who want to design systems, secure systems, and secure and robust systems. That's basically what it is. And this is a known thing. I am going to do a quick animation. So when I was doing PhD about 20 years ago, so that's a age of embedded systems. Everybody thought, okay, that's it. And before that, maybe the people before me, maybe my advisors and their lifetime, it's general purpose systems. So that's the research domain. That's where challenges are. People are focusing. But as we go along, we are looking at IoT, and names are changing, their requirements are changing, and everything is changing. But from a security perspective, the question is, how do we minimize the vulnerability of these diverse and complex computing systems from malicious attacks? Now, as you mentioned about malware, so that's also a problem. Malware, ransomware, adware, spyware, there are so many of them. Now, they may look simple, but they are actually not simple systems. In fact, many of the devices you see here, their complexity is much more complex than supercomputers 20 years ago. So they are not simple, they're very complex, they're diverse, and they have extreme kind of requirements. And although iPhone or the Samsung Galaxy or whichever, those are the most secure devices, I'm going to talk about how vulnerable even they are. But now you can imagine, what about the other devices which are not that secure? And what makes it even worse, some of these systems are connected. Whether all the devices in your house is connected, I can open my door from my phone. And these days it's very common in many countries and many communities. Everything is connected. That means an attacker, if they hack into one component, they would be easy to get into access to other components. And typically they are going to choose or hack the component that's least robust. So then the problem of security verification becomes even more complex. You already have the complexity. Now you have an environment of billions of complex, error-prone, and communicating devices. And what is even against us is the design cycle. 20 years ago, a typical design cycle used to have 3 to 4 years. And that means we have dedicated 1 year for verification. We don't used to call them security verification, but nonetheless, you have 1 year, whatever you want to do about it. Today, most devices have less than 1 year lifetime. From your phone version X to phone version X plus 1, it's really 1 year. So if you have total 1 year life cycle, sure, you started designing little early, you are using last year's configuration and whatnot, but still you don't have whole year for verification. So then you have under extremely aggressive time to market requirements. I can keep go on and on and on, but point is that's why security vulnerability or security verification is an important problem. What I want to, I want to pause here to hear any of you have any questions. Only Ashrafi and Shashwat made their camera on. If you feel comfortable, make camera on. It's only few people. I will feel comfortable to see you, talk to you, and make it as interactive as possible. Anybody has any comments so far? Okay. So what I want to illustrate now to you is that the most secure component that you are carrying or anybody carrying is your phone. And it has all kind of features that protect. And let me tell you, even that one is so easy to attack. And typically, if it was in a physical room, I would have told you, if you give me in writing, you are not going to sue me. I can just hack into your phone. I don't need your password. If you allow me to touch it. If you don't allow me to touch it, I still can do it, but it's going to take me some time. And throughout this presentation, I'm going to demonstrate that. But you might say, well, what's the catch? First of all, magicians never tell the secret. I'm still going to tell the secret. If you are going to, I'm going to tell the first secret. Please don't ask me the next one. So for example, one of my famous security researcher traveling with me for a conference in the flight, and he said, I don't believe you. I said, okay, give me your phone. By the time he handed me the phone, I already logged in. How did you do that? I said, your hand has whatever amount of oil, so I can already see how did you, whether it's a Z character or whether it's a V character. Only thing I did not know if you're going from left to right or right to left. So I had to try only twice, less than few seconds. Then he said, oh, what if I remove the oil from my finger and then you are not able to see it? I said, look, magician doesn't tell anything. I already told you at least one of them. If you ask me the second one, I'll tell you the second one. Then you say, oh, if I do that, what do you do? I'll keep on doing. And what am I going to keep on doing? That's what I'm showing you. So when you want to attack, basically whether you are, now, when did I get this idea that things are so easy to hack? I got the idea when I installed a calculator in my phone because I didn't like the default calculator. And calculator said, do I have your permission to access your contacts? And I'm like, why on the earth a calculator wants to access my contacts? And then something occurred to me. Wait a minute. If somebody has audacity to ask me for my contacts, how do I know that it didn't access it already? So then I started looking at what are the vulnerabilities, and there are so many of them. And through each of them, I can attack to your device. I can. And even if you subscribe premium rate services, my only obstacle is I also have to buy that premium rate service from that company, but I can still attack. It makes it a little harder. I have to pay a few more dollars, but I can attack. And then, of course, the legitimate attack point is I can pretend I'm the debugging person. And these are legitimate access points. If your phone is not working, you take it to a fixing shop. They are not magicians like me. They are not going to do, okay, I'm blessing this phone and this would be correct. They need to dump certain data. They need to analyze data. So then there would need to be debug port. So those are legitimate places. Now attacker can pretend as a debug person and use that feature to dump the information, and how, what, as I go along, you have to wait for me. And I'm not going to spend a lot more time talking about it, just to say, if you allow me to, if you download some app, it's already attacked. And now you might say, well, I have all this checker security, and you just say, I will say, just forget it. And if you are good at in RF and communication, then it's a gold mine. So I didn't do the laundry list of what kind of attack I can do, but there are many. In fact, just by looking at how much battery you have in your device, that information is enough for me to mount an attack. So sensor information, that's a significant attack point. Now, so I'm going to keep on moving forward. Now, this is a known fact, hardware domain, these problems are there for a long time. And I'm taking some pictures from my collaborators. I do have their permission. So this is from Canon, this is from Cisco router, and this is from Honda car. And all I'm saying, I intentionally wrote which one is counterfeit, which one is genuine, because sometimes it's impossible to figure out which one is what. And in fact, in one of the case, the fake one looks more genuine than the genuine one. Because if you're photocopying some book, if there is a typo, it's easier for you to fix. You just fix, make it nice cover and all stuff, because you're not doing actually real work. So these are a serious problem. If you buy a new camera, new phone, and it's not working, you probably know what's going on. So now I'm going to zoom into the context of what I'm going to present today. What I'm going to present today, when I say hardware, I'm primarily talking about system on chips. I'm not talking about processor. I'm not talking about controller, not talking about memory individually. We can discuss as I go along, but I'm talking about a set of components that are fabricated into a single integrated circuit. How is it different? If you open any computer from 10-15 years ago, you are going to find a motherboard, and that motherboard is going to have a lot of components. Think of taking that whole motherboard and creating one integrated circuit out of it. One, that's it. That's the system on chip. And it has all kind of good news. It's one tiny chip, less area, cost effective, better performance. But the problem is, these days, no company, maybe some except rich companies like Apple, even then I'm not sure if it's 100% sure, because they don't publish too much, or if anything, nobody can afford to develop all the components in-house in time with highest quality. That means if you're building a system, you have to rely on some digital signal processor, likely coming from Texas Instruments. You have to rely on certain processor, low power processor might be coming from company ARM. So you are getting software from somebody is doing your layout, somebody is fabricating your device. So I cannot tell you which company it is, but if you read the book, you might be able to figure out. So I took a design, system on chip design from a company, and tried to plot where the components they got it from. So basically, I can show the animation. Actually, it's not static that they got processor from here and memory from here and integrated there. Actually, they got something from here, then it went somewhere for synthesis, then it came back here. Then so it's just traveling all around the world in 65 days or 365 days. It's basically traveling all over the world, touching different companies, different groups. So then trust become a significant issue. Am I saying the world is full of bad people? I'm not saying that. All I'm saying is, even if in your company, two groups are designing processor and memory, and your responsibility is put them together, are you going to verify it? If you say yes, then my question is, you are not trusting your friends, your lab mates, next cubicle mates. You do. It's just that you want to make sure when you put them together, do they work? Because none of them tested putting them together. I'm saying same thing here. I'm saying whether you trust, don't trust, doesn't matter. Check it. Put them together, check if they're secure and trustworthy. If they are, you have nothing to lose. That's all I'm going to talk about in tutorial. I'm not taking a position, there is a country not trustworthy, there is a fabrication facility. Some people take that position. This tutorial is not to make a politically divisive statement, rather to say, let's assume everybody is trustworthy. Just check it, just verify it. That's all I'm trying to do. Anybody has any questions so far? Okay, so that's basically my way of looking at it. When you are looking at all these components, whether at the system level or system on chip level, whether individual component level, even if it's printed on it, the logo, trust me, please don't. Just check what it is. And how do I check? That's the whole tutorial. What are the other problems, roughly speaking? There are many other problems, and those I'm not going to focus too much. I'm primarily focusing on whatever I'm going to talk about, mostly in either design layer, whether you are designing a transaction, system C transaction level model, RTL, gate level, layout, maybe fabricated chip. That's basically my scope. But you do have other problems. I'm not going to talk about whether it's overproduction, whether life cycle, it's supposed to be thrown, somebody picking up the chips. By the way, that's $1 billion industry, taking the chip, recycling it and selling it as new. So those are also a lot of other problems, reverse engineering and all that stuff. I'm not talking about those. All those supply chain security, reverse engineering problem, and all those stuff I'm not talking about. Overproduction and recycling and whatnot. But those would be different tutorials. So then whatever I'm focusing, how can I kind of summarize? This is my summary of the issues. Either the component you are designing, would somebody be able to steal it? You came up with a nice design of a processor. Can somebody steal it and fabricate and put their own stamp? Can somebody just reverse engineer? You gave a chip, can they layer by layer figure out what the chip is doing and got the RTL or whatever information, and then they just sell it as their own? And then majority of the example I'm going to take from malicious implants, which is hardware Trojan. But nonetheless, many of those ideas, if you're applying on the, some of them are applicable in the RTL level, gate level. If somebody gave you a layout, or can you in reverse engineer and figure out what's the original description? Now let's focus on hardware Trojan. What is a hardware Trojan? Can I see hands? How many of you worked in hardware Trojan? And the way you show hand, go down and there is some motions or emotions, and then there is a raise hand. In your bottom area, when you have reactions, click on reactions and then raise hand symbol. Okay, nobody is raising hand, or you are not finding it. Either way, so let me then briefly talk about what are the hardware Trojans. So hardware Trojan, as the name suggests, these are malicious implants. This comes those mythical days of there is a beautiful lady in Troy and Spartan stole it and there is a fight. No matter whatever the story is, it's basically implanting a vulnerability. So here we are not showing the actual whole design. What we are showing is, let me annotate right here. So let's say you have a huge design, but in the design, I figure out two of the signals are very rare signal. How do I know somebody is rare? You simulate it. And then you print how many times A is 0 and how many times A is 1. If A is 0 for most of the time and A is 1 only less than 1% of the time, then we can say A equal to 1 is rare scenario. If 1% is rare for you, if you think no, 1% is not rare. But if you are thinking A and B would be 0 and 1, 50% of the time, that mostly doesn't happen. It can happen for many signals, but there are many signals where there is a clear bias because the way you design the circuit. What an attacker is likely to do, figure out what those rare variables, pair them up and put it in an AND gate. So if the probability of this is 0.1 and probability of this is 0.1, then you are creating a probability of 0.01. So it's basically it become rarer by making AND. If you put a lot of them, if you put 10 of them, it's a probability of activation in 10 to the power minus 10, which is extremely rare. Now, so that's the whole idea. You want to create a scenario. This is a trigger condition. If this is true, what will happen? Let me clean it up. Sorry. So what is happening is this is the trigger condition. And originally the value was supposed to be ANDed and supposed to go to the output. So this is the design, this is the functionality, this is functional output. And this particular Trojan changes functionality. That's its malicious intent. And what it does when trigger is 1, it basically flips this value. So only addition the attacker did is this gate and this gate. Everything remained the same. That's basically, of course, it's disconnected this link. So it can connect, is disconnect. That's not relevant. There are many ways of implementing this, but key idea is if a very rare condition happens, I want to change certain functionality. Now you might say, give me an example. Let's say traffic light controller. It's supposed to be green under specific scenario when I'm driving. It's supposed to be red. Somebody makes this side green so that other person can come and hit me. That's all you have to do. Change the functionality in a very specific situation. There are denial of service attack, information leakage attack, many other form of payload. But Trojan has two parts, trigger and payload. Now, combinational I described, this is the easiest one. Now you can think of sequential. Think of a counter that's counting for a very specific value. That is the trigger. And again, payload would be similar scenario if it's a functional change payload. So anybody has any question with the word trigger or payload? Trigger is when it gets activated. Remember, it's not activated all the time. If it's activated all the time, during your normal verification, you'll be able to detect it. Then attacker has no place to hide. The intention is you would be able to hide it, and you won't be able to detect this. And I'll come to that why you won't be able to detect it, even if it's rare. What's the problem? I'll come to that. Any of you have any questions, please ask. Nobody is saying anything. That's not a good sign. Let me ask Ashrafi. Ashrafi, what's the fundamental difference between triggering by combinational Trojan and sequential Trojan? Can you, these are circuit level information. From a computer science perspective, can you use a different term and explain this to me, how they are different?
Yeah. What I understood from your description was for combination, we have trigger, our own trigger. But for sequential, we use the input itself as a triggers. Is that correct?
That's actually more interesting observation, but that's not correct. And the thing is, you can use input also as a trigger, which I didn't talk about. That's actually very interesting thought. Thank you for pointing out. But if I go from a computer science perspective, this is how it look. So this is like for ECE, EE people to understand. From computer science, think of a program which has a lot of variables. Some of the variables are rare. You take a combination of those variables and create that as a trigger, and payload is whatever is payload. Sequential is, think of a state machine. You have a state machine where one of the state or one of the transition is very rare transition. You use that transition as a trigger. And at that time, you do whatever you want to do. What you want to do is the payload, malicious activity. When you want to do, that's the trigger. Right? So basically, now, if you are the system level person, then this is how you want to visualize it. All these components are coming from different companies, and many times they are black box when you are integrating. You don't have access. So you cannot insert a Trojan if you're an attacker. What you can do, you can observe certain BAS activity, what's going on, who is talking to whom. And when you see certain information, you say, uh-oh, now I think memory has the key in the unencrypted form. If I read that memory location, I think I'll get the key. Then you read that location, or you flip that location. If you think somebody else is reading that value to make a decision, locking or unlocking, you flip it. Whether you flip it, whether you read it, that's up to you. But that's how you'll insert Trojan at the system level. And there are Trojan, they are always leaking, called moles. And you might say, wait a minute, now, few seconds ago, you said if it's always leaking, it is easier to detect. What is the story? This is kind of side channel Trojan. Trojan, where payload is side channel. It's leaking, but the assumption is the attacker inserted this during design time. But when you are computing, they're holding the probe on top of it so that it can get some electromagnetic emanation or some kind of side channel signature, which I'm going to talk later, so that it can gather that information, so that it can figure out what's the key. It cannot go inside and read and flip. Its payload is side channel emanation. Now, there are a lot of attacks, of course, there are a lot of attacks, and side channel attack is very common, and probably by spending somewhere in the range of, I would say, $10 to $100, you can set up this, assuming you already have a laptop. And sometimes you don't need oscilloscope. Even your laptop with the app can work as an oscilloscope. So basically all you do when a computation going on in your friend's device, I'm showing a breadboard, but it could be somebody's computer. You basically read what power it's consuming. You don't need to know any internal details of anything else, just the power it's consuming. And then you figure out what it's computing, what's the key, and you can figure out a lot of stuff. How do I do that? When you are plotting the power, the way it's consuming, you also know who consumes how much of power. If you are doing simply addition or subtraction, you need this much of power. If you are doing squaring, this much of power. If you are doing squaring and multiplication, it needs a little more power for a longer time. Just by simply looking at it, you can figure out what computation is going on. First thing is, it's still a valid attack. If you can figure out if your friend is running insertion sort or bubble sort, you already got some information. Once you get the information, okay, where am I? Is it in the if statement, key exchange, what's going on? And many times, for example, elliptic curve cryptography, if you know that module, it basically implementation has, I'm writing something, can you guys see it? On the
Yes.
yeah. So in the key itself, there are some operations that are based on what key value right now it is. And if part has a lot of stuff, and then maybe else part has only one instruction. And why that's important? Because if you are consuming a lot of power at this time, then you know you are in the if part. So then you know that particular ith key bit is 1. So of course, aren't there any defenses? Of course, there are differences. People, this is already well known. Timing attack or even power attack, you take longer time. So people try to add some junk instruction here to kind of balance them out. So it's a cat and mouse game. When you know the attack, you try to design such that that attack is not possible. So let me take another extreme example before I move on quickly. So another example is, let's say you say your friend says, I'm not going to give you access to my computer where you will just measure the power. Why should I do that? Right? Praveen, I'll come to your question. Give me a minute. Why should I give access to my my power power port? I don't want you to hack my thing. It's like, I don't want you to come to my house. Can anybody tell me why I can still do power side channel attack even if your friend did not allow you to connect a power monitor to their device? How can I still attack that computer or that system? Any of you have any idea? Subitsa, do you have any thought? The idea is, it simply comes from Kirchhoff's law. If you studied Kirchhoff's law in your undergraduate, irrespective of your specialization, Kirchhoff's law basically says, if nobody else is drawing power in the network, even if I'm connecting from another room, let's say your friend is working from this room where I am, and you are sitting next to my room. If you connect in the power monitor in that room power supply, you'll be still able to figure out how much power I'm drawing. And there are a lot of assumptions. In that power connection grid, in that building or that floor, other people are not drawing power and all that stuff. I'm saying no matter how difficult you make it, it would be still possible to figure out what's going on. And there are a lot of work going on in some of those areas. Prabin, you had a question. Go ahead, please.
Sir, you were talking about the side channel analysis. So I have seen some work regarding the polymorphic code generation, where they will generate different instances of the crucial part of code so that they can fail the side channel analysis.
Yes. So there are defenses. There are attacks. There are defenses. But the power attack that I'm just talking about, this is like 20-year-old story. Paul Cocker. But then there are differential power attack, a lot of sophisticated one.
So my question is, those polymorphic code generation techniques came long back. So is there any potential still there available, or we can say still any potential left for those kind of solutions against the side channel? like a generation of polymorphic code?
It is actually, people do that in malware. They actually use polymorphism to bypass the detection technique. Today, as we speak, they use different deviation and obfuscation capabilities, because if you know that hardware performance counter value, if it becomes too large, that sounds like a malware attack. So then I want to put a lot of junk code and polymorphic behavior so that hardware performance counter value is low, or whichever you are looking for, I want to fake it if I'm an attacker. So polymorphism has huge place in malware, ransomware, in many domains. When I talk about Spectre and Meltdown, I'll briefly touch upon polymorphism also. Okay, so let me now go straight to now verification. We kind of motivated a lot, but those components are needed. I'm going to use all along. So why security verification is challenging? Fine, there are the problems. We know the problems. We check it and it's done. What's the big deal? The way to understand this, let's go back to the simplest example of a Trojan. A tiny trigger and a tiny payload. And I'm taking a tiny design 8-bit ALU which has 451 gates, and there are 10 to the power 11 possible 4-input Trojan. Even if the attacker told you, I'm going to insert a malicious implant using an AND gate or NOR gate which has 4 inputs, this case it's 2 input. Even if attacker told you, first of all, attacker will not tell you. Even if the attacker tell you, you still have to check 10 to the power 11 possible combinations. And it's actually much bigger problem than that. I'll come to for a moment. A design with few hundred gates, we are talking about 10 to the power 11 possibility. Now you can imagine with millions and billions of gates, lifetime of the universe, you won't be able to check it. It's not possible. But I'll explain even a simpler way. If you think of an adder, 264-bit inputs, if you really want to activate all possible scenario, you have to try 2 to the power 64 multiplied by 2 to the power 64. That's 2 to the power 128, which is 10 to the power 38. If you look at this number, you know it's simply impossible to try all possible inputs. And because it's a rare of the rarest scenario where attacker inserted, and attacker exactly know what input combination will activate it. That's why during your traditional regression validation shoot, it's highly unlikely that the Trojan would be activated. If the Trojan gets activated, then you will be able to detect it. There is a problem. Problem is you won't be able to activate it. That's the problem. Any of you have any questions? Input space, this is classically known as input space complexity in verification domain. You have so many exponential inputs combinations, you won't be able to activate the Trojan, which is under a very specific rare combination. And of course, if I extend the argument, a tiny adder ALU is a lot bigger than that. It's not up to the scale. You can imagine processor is much more complex than that. Systems are a lot more complex. If I am having this much of problem, impossibility problem in adder, forget about verifying a complex system. Now, so basically verification has been known to be a grand challenge since 1990. So it's not surprising that this is a problem. Now I'm talking about functional verification. Security verification is even more complex. Can anybody tell me why? San, can you tell me why security verification would be more complex than normal verification? Or more complex than functional verification? Anybody else wants to try? It's a simple idea. When we draw Venn diagram, when you think of functional verification, let's say traffic light controller, you kind of say, well, what needs to happen? If a car is waiting, there are a few scenarios you list. The scenario that should happen. But rest of the universe is the security problem. This is the security problem. These are the expected behavior. What is expected out of here? I'm not writing it properly. Expected. This is the expected behavior. And all the unexpected behavior are the potential vulnerabilities where attacker is most likely going to insert, including undefined states and transition, unspecified functionality, and all over the place attacker is going to insert the stuff. And people typically verify all the expected scenario when they do functional verification, and security verification becomes a tremendously hard problem. Any of you have any question before I move forward?
If it is so difficult to verify the whole system, then is it necessary to do so? I mean, for the device that is not so, how do you say, important.
No, device is very important. When you are flying in an airplane, is it not important that it safely lands the airport you want to land in?
Yeah. For the important device, it is necessary to do so. Then maybe for the normal one, that is not so.
There is no. Give me an example of a normal device. Give me an example of a normal device where you believe. So first of all, I'm still talking about functional verification. If you are designing an adder, it better add correctly. Right? All I'm saying, verifying an adder is impossible. So the airplane you are flying, the chances are all possible situations has been verified completely is 0, not even 99%. It's not possible. So people only verify the absolutely critical scenario. For a phone, it's a different story. If you ignore for a moment security issues, that you are doing a banking transaction, somebody is stealing your money from your bank, even on functionality level, it's a different dilemma. You want to, a company like Apple or Samsung wants to make sure somebody is drinking, driving, texting and phoning. Are there any problem? These different combination of scenarios. But when you are designing a processor, you do not know where it would be used. So you do not know the use cases. Many scenarios, you know the use cases. You can check the use cases. But many times when you are designing a system on chip, you may or may not know where it would be used. So then your scenario is really high. But anyway, that's a debate we'll do some other time. But the thing I want to tell you that we need to verify whether we can do everything or a small set, we need to verify it. So basically we cannot give up because, oh, if I can't do completely verify, so I'm not going to check it at all. We still need to check it whatever we can. And all I'm going to cover what people are doing today. So okay. I'm going to, you're welcome. I'm going to skip these known problems. Those of you are working in verification, these are like standard bread and butter, you know. What to verify, how many tests to generate, how do I debug? If I debug early in the design cycle, it takes half a day, 1 day. If you have an integrated circuit fabricated and you find a problem, now you have to debug and fix and refabricate. It's $1 billion cost. Few companies like Google and Apple, they can fix bug and refabricate. Many other company will go out of business if they have to second time fabricate, third time fabricate before they sell the chip. They will go out of business. So it's all known problems. I'm going to skip. And also in terms of verification, people are doing whatever they can do. In 1995, a typical SoC design used to be 1 million lines of gate, about 20 engineer years, and about 100 million test vectors they used to run. In 2022, this is a published result, billions, test vector is trillions, and this number I came up with. There is no published result. Published result is up to this far. So irrespective of what it is, people are doing whatever they can do. You might think, why trillion? Why not some other large number? I don't know, come up with gajillions. Because the thing is, it's not gajillions of tests you can run in cloud, even if you have a lot of money running in parallel. When they fail for the same bug, all of them will start failing. Somebody has to sit and try root causing what the problem is, and that becomes a nightmare. After spending a lot of time, you might figure out all the hundreds of errors are actually came from the same bug. But so it's not simply like, okay, you run a lot more and problem will go away. And you fix a bug, other bugs will problem. Now that I talk about security validation challenges, my next context or concept is, okay, I'm already doing verification. When I wrote a C program, I'm already doing GCC or Java, and I'm running with some input. How is it different? So the way it's different, if you are working in verification group or other people are working, they have a bug model or fault model. Some test engineers are actually writing tests. Somebody is writing what need to be tested and somebody is actually writing tests. In security domain, we have these kind of terms. We need some threat model. What are the threats? What are you scared of? You are hiring a bodyguard. First, you have to tell what are you scared of? Scared from the people who are inside your house? Scared from strangers? Scared for somebody who would be doing kidnapping you or your kid? So you need to define the threat model right. If you say, I have no idea, it can come from anywhere, from satellite to different country to, so then it becomes a difficult problem to manage. You have to define the threat model. If threat model is wrong, please don't expect the detection techniques will work. Then what are the metrics? Even if I developed a solution, a tool, how do you know it's doing a good job based on the threat model? What are the benchmarks? When I'm designing something, I don't have real people using it and real people attacking it. How do I create benchmarks that would test how good my detection techniques or verification techniques are? Am I verifying correctly, or I'm just saying, oh, I verified, give me whatever $1 million, I'm done? How do you know? Why would you give money? To your employees, to somebody else, subcontractor? So let's talk that briefly. So this threat model space is huge. There are a lot of people working. I'm working for many years defining. So to give you a starting point, this area is not as robust or good yet as functional or manufacturing testing domain. Manufacturing testing domain, there is a stuck at fault, delay fault, all these nice defined fault model people use. In functional verification domain, you have code coverage, statement coverage, branch coverage, FSM coverage, all that nicely defined stuff. There is not so much of clean definition in the security domain. And I'll give you an idea why and what has been done. So for example, if you are doing even simple Trojan detection, remember Trojan is one type of vulnerability. There is so many other types of, even if that for simple type of vulnerability, if it's in the insertion phase, it's a specification, RTL or design phase, and register transfer level design, and it's triggered internally or externally, and what is it doing, and all that we put in, then basically we can define the threat, who is it doing and what they are doing, and the kind of Trojan model I have shown, the rare nodes and trigger, and that applies to the scenario I highlighted. But the scenario I did not highlight, those are also attack surface. Those I did not define what are the threat, how do I detect, and what will happen. So there is a lot of threat related work, and every time I go through a slide, I put a paper title, and you can go through recording later to get the title and read and ask me questions. Send me email, I always reply within 24 hours. So now that we have a threat model, what we are scared of, then okay, I know what you're scared of, but how do I compute whatever tool you are running? Remember, even functional validation domain, whatever metric you use, those are still useful here. You still have to check for those. But in the security validation domain, if you assume that an attacker is going to insert Trojans in a suspicious area, hard to detect area, then you want to do something like rare node coverage. How many rare nodes are there in my design, and whatever test cases I generated, whatever testing I have done, how many of them I activated divided by how many total possible are there in the denominator. That's a metric. We may not agree that's a good metric. There we may decide there might be a better metric, but that's still a starting point. That's a metric, and this metric may not look like the metric you are accustomed with, but it's still similar. So for example, in the manufacturing testing domain, total number of faults and numerator is how many faults you have covered so far. And covered meaning if fault may not exist, but you ran those test cases and you figure out that's not a problem. And then there are, we can go for laundry list. And again, if you want to read, so this is a work, my 2019 work in design automation conference, some of the initial work, what a trust matrix should look like. And there are a lot of follow-up work you can also improve. I want to take a very specific example that you can relate to. So this is an example of, this is a tiny part of the automatic encryption, advanced encryption standard, AES module. It's a very tiny part of finite state machine of AES module. And what I wanted to show is, what do you mean by tool and metric? I mean, connect the dot. Tell me, if I want to do something, what exactly should I do? You take the RTL design, you extract the finite state machine, There are like open source tool like EOSys and Icarus Verilog that can give you extract FSM, and then you can implement different stuff. What am I implementing? That depends on what's your threat model you're thinking. For example, in this case, we thought don't care states, don't care transition, and laser fault injection. Those are my vulnerabilities. What is a other stuff you probably know? What is a laser fault injection? So think for a moment, this is a state which is encoded as 000 after synthesis. Let's say this is encoded as 010. Just randomly, let's keep giving name. So the idea is you want to wait for certain key, you want to check certain things, then you're going to, let's assume this is a initial state and this is the final state. So how do I go to the final state and start the banking transaction without going through any of those? If you look at the number of bit difference, this is 000, this is 010. If I can flip this bit to 1, I got the gold mine. I already moved to that state. You might be saying, well, whatever state machine I have learned in my life, you still have to do this transition, or actually there is no transition from here to here. You have to go through this and that and that and that. What are you talking about? To understand that, you need little bit of digital logic. The way these are implemented. So this is a register and this is the combinational logic. And initially this register has a value of 000, which is this particular state. Now, through the computation, it's supposed to go through this, and this is supposed to be 010. When you get special privilege level, you can access certain stuff and all that. All a laser fault is doing, it's throwing a laser on top of an integrated circuit, fully fabricated, very carefully, that can flip this bit inside, deep inside the design. If you can flip this bit, that means practically you are already here. Because this is how it's implemented in real hardware. A sequential element followed by a combinational element. You flip a bit and you are done. Now, what's the protection? That's different. But my job is the verification. Protection would be laser has a capability. Today, in academic world, or at least the systems we have, we can flip up to 2 to 3 bits carefully. So that means if the difference between this encoding is more, Hamming distance between these codes is more than 3 bits, you won't be able to attack using today's technology. That's all it means. But you still need to verify, is my finite state machine protected? How vulnerable it is? Because it comes with a cost. You would have been encoding with 3. Now, if I say add 3 more bits, that's expensive. That's expensive in terms of area, power, performance, and whatnot. So is the context clear? What does it mean by detection, threat model, and all that together? This is the example I want to do. Let's ask me some questions on this before I move forward. This is a simple context of finite state machine vulnerability analysis. And it's a very simple scenario, laser fault injection. That's my threat model. And I talked about in that, what do I analyze? And I also talked about what kind of defense mechanism you can apply. Assuming the laser has a capability limitation of flipping up to 2 or up to 3, then you can do something. If laser can flip any number of bits, there is no defense possible, at least from state encoding. So what is the attacker's goals? Attacker doesn't want to go through any of these steps. Straight go to the approved. It's like you don't want to apply for bank loan. You simply approved and take the money from the bank and then vanish. Any questions?
Sir, we are talking about the flipping bits in the DRAM, right?
It could be DRAM. No, actually, we are not flipping DRAM. We are flipping in the register. So,
Register.
yeah, but it could be a state machine inside the memory. You can make that argument. But yes, you actually brought up a very good point, knowingly, unknowingly. Laser fault is actually works very nicely in DRAM. It's actually harder to do it in the main logic area, because finding where that register is and pointing the laser precision, that's much harder problem. Much harder problem. And we are talking about 2D. When you have a 3D fabrication, all that is going to be difficult problem, and people will come up with different way of attacking. But we are talking about it. Go ahead, please.
I was working with something called row hammer attack. So where using the software, And based on the timing latency, we find out the area in the RAM where flipping bits is possible. Like we refresh and read and write in such a faster way so that in the adjacent rows, some bits get flipped.
Yes.
So same thing can be applied here also.
Yes. So you could do row hammer attack to flip the bit. But that would only work in main memory. This we are trying to. So basically, the point is, why do you want to do row hammer attack if you can directly go and flip something, right?
Yes.
So in the row hammer attack, it's basically you are going through microarchitectural cache and main memory access using the valid instructions without having the laser capability. So that's why I'm saying your threat model, if threat model is row hammer attack, the verification techniques are different, defense is different. I'm talking about laser fault injection attack, which is the most latest and greatest attack possible. You simply point and you just flip. Now, those of you on the line, I'm seeing Bivas new in the line, and Subitsa is not talking. So can you tell me in real life, your personal life, can you, if I call you as a computer or a system, you as a brain, your ear, nose, those are the sensors and all that, what kind of attack somebody can mount on you? Or me, if you feel uncomfortable talking about you, what kind of attack somebody can mount on me? And this has been successfully used for thousands of years all over the world. Nobody saying anything? Anybody never heard of a term called guru, spiritual leader? They are doing it consistently for thousands of years. If you have a guru, please don't get offended. It's a mental attack, whether attacking on your fear, attacking on something you have did in last summer, I know, whatever it is, manipulation technique, whether it's for any celebration, they are collecting receipts for money to raise for certain thing they want to do, some puja or celebration. It's that technique. Whether they want to make you, oh, if you don't pay, I'll tell the society and you'll look like such a cheap person. That's the technique. So gurus are doing it long time, political leaders are doing for a long time, and everybody else is doing. Parents are doing on kids, kids are doing on parents. It's a reverse psychology attack and all that. These are actually completely identical and isomorphic. If you understood that problem in human domain, you understood this, and vice versa. Any attack you see here, that can be applied on human being. If I'm little closer to you and your mouth is smelling, I can figure out a lot of stuff by looking at your walking style. If you allow me to touch, by looking at your temperature, I can figure out a lot of stuff about your device. If I irritate you a little bit, how you react, I'll be able to tell you your state of mind. So, but I should be allowed to irritate you without getting killed, of course. I don't want that to happen, right? So anything I talk about, you will be able to relate to human as a system on chip, and all of them apply. And there are a lot of research efforts even in that direction. I'm not actually making it up. I wish I was. So now you go to the FSM vulnerability, the trust matrix. This is a little more complicated, but don't go by the equations. If you know the number of bits, encoded bits, number of states in all that stuff, you'll be able to define what is the metric of percentage of don't care states, percentage of don't care transition, percentage of LFI vulnerability. And your idea or goal would be to reduce this number. You redesign your finite state machine so that these numbers goes down. That's the validation analysis problem. And if time permits, I'll talk about other aspects like power thermal violation. How can that be a security vulnerability? Real-time violation. How can that be a security vulnerability from an attacker? How do I verify it? If time permits, I'll get to that. Now, last thing is benchmark. So benchmark is actually important. Most of us, actually one of the researcher recently got LeanPack developer for developing a benchmark, got the Turing Award. Turing Award is like Nobel Prize in computer science. So Jack Dongra came up with the idea of LeanPack, a collection of benchmarks. And he became Turing Award winner. I'm just saying benchmark can get you a Nobel Prize. If you do it in the right time and community is using it, and that changes the whole landscape of in LeanPack domain, it's basically the kind of all kind of linear mathematical algorithms and benchmarking of that. But there are a lot of static benchmark. TrustHub is one website. I'm not endorsing anybody or other way around, but you can go there. You can find lot of types of vulnerabilities in design level, layout level, and exact example on RTL design and layout design. You get exact of those. Golden one, no vulnerability, vulnerability inserted one. Now, if you have a tool, run it and see if you can detect it. You have thousands of benchmarks, run it. So only thing is static benchmark, you have a bias. Now, let's say you are a company. One of you are from Synopsys. Which from Synopsys? Okay, Ashrafi. So let's say you are in Synopsys, right? I know Synopsys is a tool company, but you developed a tool and you want another company, let's make it up, Intel, to buy it. Why would Intel believe your Trojan detection tool? You said, oh, I run in this benchmark and detects 100%. What they really want in their design, they want to insert Trojan and they want to see whether your tool or Mentor Graphics tool or Cadence tool actually do better. How the static benchmark doesn't give you that capability. You need dynamic benchmark. You need the capability to, you want another tool that you want to run on your design that would insert the number of Trojan or whatever vulnerability you want to insert, wherever you want to insert, what type, what trigger, what payload. Sorry, excuse me. And then you want to figure out whether the tool from Cadence, Synopsys, Mentor Graphics, whichever is doing better for my design, for my Trojan, the kind of threats I think may happen to my design, and I don't want to give it to anybody, then dynamic benchmark would be, or benchmarking would be more useful. Again, all of them, you have pointer to starting point, but as you can see, this work is like 3-4 years old. There are a lot more works after that. So this was one of the early work on dynamic benchmarking. Now, what kind of stuff you do, this laundry list, it's not important. You can do a lot of stuff. Here are some examples where, how they look. I'm going to skip. And this is a logical point for any of you to ask anything about introduction. All I have covered is introduction, but I set the context so that I can meaningfully discuss about simulation-based verification, side channel analysis, and formal method. So I'm planning to have a break in the middle, but if all of you guys think you want to take a break now, that's fine for 5 minutes. Otherwise, I'll continue. Bibhas, you didn't ask any question yet. No questions? Okay. Let's begin. So simulation-based security verification would be the easiest one, because whether you come from software domain, hardware domain, you do simulation all the time for functional verification. But if you are not from officially from verification domain, this information might be useful. The verification problem is basically, if you specify something, one model you have, that's it. Give it or take it. That is, whatever the term is, it's not important. We are asking, is this what I want? Now, question is, how do I know? If I call you, oh, this is a good professor or this is a good student. Good with respect to what? If there is no reference, if getting 100% is good or 90% is good or 50% is good or just passing in the exam is good, what is good? So when you are in a specification, you still have to have some notion of goodness. But when you are doing implementation verification, you need to have a specification. Now, this is a chicken and problem. Verifying anything is impossible exhaustively. But at some point, you have to believe, okay, 60% somebody getting in exam is a good student. It's debatable, arguable, but let's just fix it. Because if you don't fix, next time you want to admit other students to your university, department, company, whoever, you have no clue. So when you have a, let's say, get level implementation, you have to assume either the C model or RTL or transaction level model, whatever it is, something is golden. You want to compare with that. If you have nobody to compare with, the game ends, both for functional verification as well as security verification. Right? And in security verification, problem is bigger. If you want to check side channel, which I'll come in a minute, if you don't have a golden chip, how are you going to compare side channel signature, power dissipation, electromagnetic emanation? Whom are you going to compare with? If you have a golden chip, why are you talking about something potentially buggy? right? It's a joke. So typically you have only one model. In functional domain, you may have two models. In many scenarios, specifically side channel scenario, you have only one model. There is no golden model. That makes it much harder. But nonetheless, verification problem still is you have some idea of what the golden boy or golden girl should look like. Golden student, golden professor, golden employee should look like, and everybody else you are putting up to that standard and saying, yep, I can hire this person. And these are the two techniques I'm going to talk about. Simulation, that basically validate the design using a set of test patterns, and formal method is that prove certain whatever stuff. I'll come to that. What are the good part or bad part of these two techniques? Simulation, you can simulate any design. Billion get design, no problem. But it cannot give you any guarantee. Why not? Because the number of tests you have to run, that's 2 to the power number of possible input combinations, which is exponential, potentially infinite. I cannot test all possible scenario. So therefore, guarantee is outside the door. In contrast, in formal verification, it's a complete proof. It does not rely on inputs at all, but it relies on the finite state machine or internal design complexity. If your design is complex, if your finite state machine can have a states explosion, then we have a problem. So formal verification is typically applied to very small and critical components like cache coherence controller, like floating point unit, or anything else critical in your design you want to formally verify. Rest you want to simulate. So simulation based verification has a problem of input space complexity, all possible inputs. Formal verification has a problem of state space complexity. If your design is really complex, let's say number of states in a finite state machine is really too much, and if you want to dynamically expand the finite state machine under different clock cycle, then it's going to be serious problem. Any question on this very basic idea, simulation and formal, how they are friendly, how they are unfriendly? Industry uses a combination, small critical components, they apply formal verification. For everything else, it's simulation. So now putting for hardware domain, putting everything side by side, these are the three things in hardware community do. And many companies, it's done by group, but most of the places I know it's multiple groups. If you look at Intel, each group will have hundreds, if not thousands of engineers all across the globe. So pre-silicon is before you fabricate your RTL, Verilog, VHDL gate, and you are doing verification at that layer. When it's fabricated, integrated circuit, there are two communities. So post-silicon validation community that assumes there are no manufacturing defects. Are there any functional errors? You might be thinking, wait a minute, why didn't they check the functional errors or errors here? Because many errors you cannot catch when you are running, no matter where you are running. Here you actually have an integrated circuit which is supposed to run at 4 gigahertz, but RTL simulation, today's processor is 2 gigahertz. How can you run something at 4 gigahertz using 2 gigahertz processor? You cannot. You cannot run on top of the operating system faithfully. So there are many errors that will not produce unless it's a realistic environment running at 4 gigahertz. Many electrical errors, it's hard to model at pre-silicon, and they will only show up as a problem. So this is pre and post silicon. I worked extensively in post silicon. I'll come to your question, Ashrafi. In post silicon, biggest problem is getting a blue screen would seem like I have seen God. Even getting a blue screen is important. You connected and nothing is happening. Power is not getting on. So although you want to really verify the problem, but forget about it. Even power is not coming up. So now I'll come to manufacturing testing. Before I do that, go ahead, Ashrafi.
The difference you said about finding bugs in integrated circuit which are not able to be caught in RTL verification, is that true even for security? Or,
yes, security is bigger problem. I'll come to that. I'm setting the stage because it's easy. I want to say it so it as a delta, because this is easier to explain. It's the same problem. Many security problems you won't be able to find, because see, even in functional domain, anything you can catch it RTL, you want to catch it then and there. You don't want to wait for fabrication. But problem is there are things shows up. And as I said, some companies are rich like Apple. They can afford to have multiple fabrication. Other companies are not that rich. It's not that they're going out of business. They are coming up with some patching technique, microsurgery technique. There are ways to, so even a trivial example is if you have let's say 4 megabyte cache and there is a problem, you can sell it as 2 megabyte cache, turn off half of them. Even if one transistor is bad and you cannot patch it, turn off half of them and sell it as a Celeron processor or some other lower end of the story. You can sell it as. So there are many solutions. It's not that either use it or throw it. There are many other solutions. There are solutions where at the firmware level you can patch. I'm not going to go through those. And in security level, same story applies. You found a security vulnerability, you want to create a patch. And if you can create a patch and hide that problem, that's the best thing. Manufacturing testing is again alternate domain. The assumption is there are no functional bugs. You are drawing a line in a nanometer level and that line got disconnected. So you are drawing something, let me draw it here. You are drawing a line in nanometer level, but the line was not continuous. It's an open fault. Maybe you are drawing two lines. They somehow got touched each other. That's a bridging fault. And there could be stockade fault. So people are checking those stuff. But chicken and egg problem, you probably figured out. These people are assuming there are no functional errors, no functional problems. And these people are assuming no manufacturing defects. But in reality, both can happen at the same time. One can hide the other problem. But that makes it more interesting. That's why I work in this area extensively. So now moving forward, now, post-silicon validation, as I said, a problem. Now I want to bring the security context to it. Post-silicon has a lot of other stuff because you're busy. So post-silicon problem is a bigger problem. If those of you debugged million lines of software code, you do know how difficult it is to debug a problem. Although you have full visibility in the debugger, you can print all the millions of variables if you want to. It's still very hard. Now let me change the story. In post-silicon, you have millions of variables. By the way, you cannot print or see any of them. Now you go ahead and debug. Then you get the feeling. And to make it worse, it's running at gigahertz. That means in every second, the amount of data it dumps, you won't be able to store it any memory or hard disk known today. So you won't be able to replay it in simulator. If you, with that even few seconds of trace, you won't be able to hold in and simulate. Second thing is basically you have no visibility. So what companies allows is some form of trace buffer. In a million gate design, you can trace 128,000 of them. Visible. That's all visibility you have, whatever you want to do. Now, I didn't want to talk about post-silicon debug. What I want to introduce to you is this. If I'm an attacker, why would I attack a bulletproof door? Why don't I break your bathroom door? It may be a little smelly, but I want to get in. In the beginning, one of you asked me question, why do you want to verify? It may not be an important component. If you followed many attacks, you will figure out. I'll specifically take the attack on the company Target. It's one of the big company in USA. And the way millions of credit cards were stolen, the attacker actually attacked some bathroom management system that was not very secure. From that, they got a foothold. Then they connected to another system and then eventually to credit card management system. If anybody attacking a car today, most likely they are going to attack the infotainment system, your DVD player, your radio, because that's not secured. From the infotainment system, they're going to attack your ECU, electrical, the main controller. It's going to attack and so on and so forth. Then it's going to take control of your car. So the point is the same thing. Once you get access through the trace buffer and debug, then you can mount an attack wherever you want to do. So the security validation problem, or if you want to defend yourself, make sure couple of things. Be smarter than your neighbor. Make sure you lock your door and ask your neighbor not to lock their door. Lock your car door, ask your friends not to lock their car door. Your problem is solved. A thief, there are many stupid thieves, but if thief has any intelligence, they are going to steal the car where door is open. Instead of breaking it and creating a noise, they are not going to do it. Those of you have any connection to forest, born and brought up in village, you know when you're walking in the forest, don't walk last, because tiger always attacks the last person to create less noise, less distraction. Always walk. Front might be problem, leadership issue, stay in the middle. Never walk towards the end. So, but anyway, this is a cat and mouse game. What attacker will do and what will you do, and what I'm going to show how that reflects on in the scenario of verification. Any questions here? If you want to be an attacker, just attack the weakest component in the system. So let's talk about assertion based validation. I'm going to spend time on this. So assertion based validation is basically you are using assertion for verification. I'm going to talk about functional, then I'm going to go to security. And it has been used extensively in many industries. So as you can see in ASIC design, this is a study from Wilson Research, and you can see code coverage, functional coverage, everybody is important, they are used, but assertions are also used, and a reasonable percentage of design projects. So assertions are used, and same thing for FPGA based design. It's little less, but it's still assertions are still used. And if you want to read more, know more about more, we have a lot more analysis on this and recent ACM Computing Survey article on assertion based validation. But the point I want to highlight that many companies, including the companies where you kind of have Six Sigma and kind of ACI level 5 certification, and the coding guidelines includes you write one sentence in your C or Java program, 5 sentences of comments, and then one assertion statement. So it's actually that important. And what is it anyway? And what does it do? It makes your debug easier, and it allows you runtime monitoring. Here, take an example. Let's say you are opening a file in a write mode and you want to write to it. If you do this, there is a chance you might get a segmentation fault. If that directory doesn't have write permission, it won't be able to open the file pointer. File pointer is null, and you try to access that file pointer, write to it on a null pointer, it would give you segmentation fault, core has been dumped. You can debug the core, you waste your time and all that stuff, or you can put an if file pointer equal to null, then you print the statement and exit. That saves you all the debugging time and all that stuff. Or even better, most languages allows today some form of assert statement. Assert basically says, if file pointer is null, then stop execution right there, print an error, assertion failed on this line, this file, and you can see the trace and you debug just like that. Of course, debugging time may take time, but your detection of what went wrong, you exactly know. So this is the same idea for security assertion. Here I'm some behavior I'm saying what I don't like to see, and security assertion, you just list that behavior. And instead of getting into the whole theory of it, I will take specific examples so that you know what we are doing. So before I get into behavior, I need to go back to threat model. What kind of behavior am I looking for that I want to code as assertion behavior? Again, the same thing you already know, hardware Trojan we talked about, but there are so many other types of behavior that I need to do. They can be even combination of them. Let me show you information leakage and hardware Trojan together. Let's say this is a design where you have a trigger and you have a payload and all that stuff. Now, let's say there is an asset, let's say X3. Don't assume this as a primary input. Think of this as some internal variable of the design which represents the key. Or if you know this value, you might be able to figure out the key. It could be your birthday, your social security number, whatever it is, your PAN number, whatever it is, right? National ID number, whatever you want to hide. Now, the information, if there is a leaky path where information travels through something, but remember, when information travel, there is a if statement. An if statement might have a condition if privilege. So if you are a privileged user, information is supposed to flow. Otherwise, how would you debug and test? Then when a key is supposed to flow, it would actually flow. But what this Trojan will do, when it's not even privilege level, it will flip that privilege bit. It's not privilege level, it will flip the bit, so that would allow this value to transfer to the output. So the Trojan, together with the leaky path, changing the privilege check or bypassing. You can do that through laser fault injection also. And then that would make the attack happen. So when you talk about an attack, it may not be one vulnerability, boom, worked. It could be a set of vulnerabilities working together. And what is the first step in assertion-based validation? That's true for functional and security domain. You want to generate the assertions. And what do assertions look like? So security assertion. So assertion could be, is the user admin privilege? If I send a request, do I get an acknowledged? It could be immediate assertion, wherever you want to check, right then and there, like if statement. Concurrent assertion is running in parallel. You are checking if acknowledgement 1 implies acknowledgement 2 should not happen. Why not? Because let's say you have one printer, you cannot tell 2 people to print at the same time. 2 sides you don't want of the road, you don't want to be green at the same time. Only one side should be green. And this one I'll come back in a moment. So those, and if you want to know more about automated assertion generation, we have a recent article in ACM transaction emerging technology on computing systems. Now let's take very specific example, mutual exclusion, and that's many times important. Let's say you have a bus architecture, and in the bus architecture, let's say it's a 32-bit bus or 64-bit bus, and 2 people say, I want to talk, I want to transfer some data through the bus. Forget about time multiplexing for a moment. So you want to allow only one person to send data, otherwise it will overwrite and you'll lose the information. So what you want to do is you basically want to make sure whatever it is, these are the grant or acknowledgement signal. You want to put an assertion which would look like both should not be true at the same time. There are many ways of writing this. I'm showing in a temporal logic, and I did not want to discuss how to write temporal logic. What it looks like is basically saying grant 1 and grant 2 should not be true at the same time. If they are true, this is 1 and this is 1, this expression is 1, not of this is 0, assert of 0 or null, it's going to fail right then and there during the execution. At that point, I'm going to pause and ask you, why am I doing assertion-based validation? If this behavior is so important, why didn't I check in the, although I didn't talk about formal verification yet, why didn't I check formally check whether that scenario will not happen? Why didn't I do that? Why didn't I test this scenario? I generate a test pattern and check whether this 2 scenario doesn't happen. Anybody want to attempt to answer?
There could be multiple places where the signal is touched, and so this kind of tests it at the top level.
That is true, but the point is, in assert statement, whether concurrent or this, I'm checking whenever it's happening in the simulation time. It didn't happen. You ran simulation for 2 hours. That doesn't mean you have a problem. Only thing it means, the problem did not happen in 2 hours. That's all it means. But if you do formally verify, you guarantee for the lifetime. Why didn't I do that?
To save the time and space for search.
No. If you can, you should always do formal verification. Although I'm covering at the end, but this is a good opportunity for me to tell you. If the design is not too complex, state machine formal verification tool does not lead to state space explosion, do it. That guarantees forever, eternity. You want to put assertion for the scenario that you did not check, could not check. You don't know whether that would happen or not in the lifetime of the device. You put it in. Something you guaranteed. Now, many companies today, they still put assertions, runtime checkers. Even if they guaranteed, that problem doesn't exist. You know why? Because when you design something, you have a set of assumptions. When system is running for 10, 20 years lifetime, like in car, you don't know how the things are going to change or evolve over time. Many of the assumptions may not hold. So then, boom, the problem may happen. So if you can afford, this assertion would cost you area, power, performance in the real hardware. If you can afford, some people actually put in even the things they completely check. But for in general, if you can formally check, you don't need to put that assertion there. You formally guaranteed this problem will not happen. So let's take a second example. This is the get password, check password, and do the operation. We talked about it in a context of laser fault injection attack, that if my encoding is 01, this is 00, I flip this bit and I can go straight there. This you can access through Trojan, you can, and those of you know synthesis, even if in your program you wrote 3 scenarios, when you synthesize it, no matter what tool you use, Synopsys or Cadence or Mentor Graphics, it's going to create 4 states because it's simply binary encoding. Using 2 binary values, you will have 4 states. So this state you did not want to see. This state, nobody verified it. This was not in the specification. This is what attacker will use. Don't care state or unspecified state or functionality. How, what? Let's ignore that one for a moment because I don't want to digress. But what the assertion do I write here? Because really in verification, what people check? The expected scenario. I want to check this transition. I want to check this transition. I want to check. Nobody checking the transition. That's not supposed to happen. If you have n nodes, you have 2 to the power n possible transitions. Out of those 2 to the power n transitions, only n of them people verify. So you are left with so many transitions you didn't verify. This single assertion will cover all of them. That's what I wanted to show. Although it may seem like potentially infinite, if you do it right, what is it saying? It's saying, again, it's a temporal logic. It's saying from state G, there should not be any transition, no matter how, what, which way, to state O. So G implies O, that basically means this state has a transition. You say not transition. And assert property, this is a semantics that basically means it's a concurrent assertion. It's not immediate assertion. But if you ignore this semantics, that's not important. All I'm saying, from this state, there should not be a transition to this. This is a simple one. If you have a complex one, you can encode lot of states here. You can put lot of, from a set of states, there should not be a transition to another set of states, assuming there are more than one important final state. You can write whichever, but that's basically that those transitions should not happen. If it ever happens during execution, assertion will fail and execution will stop right there. Let's talk about another one. It's a very common one, and then we'll take a break. This common one, it basically says that those of you know a little bit about how people hacked in the past, how did they found the key. So any hardware works in 2 modes, debug mode or normal execution mode. And normal execution mode, as the name suggests, you know, and debug mode, they are trying to figure out manufacturing defects, this and that. They use something called scan chain to push the value, to initialize the system to a known state. Otherwise, if you want to initialize a state machine by simply applying inputs, it may take forever, right? So what initial days of attack used to look like, you are doing normal execution, you figure out when key is getting exchanged or key is in an unencrypted form in the scan chain, stop execution right then and there. And then use debug mode to dump those scan chain values. That used to be the attack. Now, of course, some of those are sealed, but let's assume you still want to put that check. The way you put that assert, you are basically saying, if you're not in a JTAG mode, which is the debug mode, then basically JTAG output should be always 0. You should not produce any meaningful value out of it. If it's producing any meaningful value at any time, that means some hoopla is going on somewhere. We need to stop it, right? So now let me finish this assertion, a few more slides. So question is, now you put the assertions in your design. How do you know they will actually work when it's supposed to work? You hired a bodyguard. How do you know the bodyguard will actually work perfectly? Hire me also to attack you, and let me attack, and let's see what happens to, am I left with 1 hand or 2 hands after I attack you? How your bodyguard reacts. You want to see that. So there are many ways of activating, and here is, I'm showing one solution based on concolic testing. Concolic testing is a scalable technique. I won't get into the detail, but you can read the related literature. But the basic idea is concolic testing is good at activating branches. So first we need to convert assertion to as branch coverage problem, and then use concolic testing to generate the patterns. And basic idea of concolic testing, if you remember, I said simulation is very fast, and simulation is scalable. Formal gives you the guarantee. Concolic testing is a combination of both. Let's say I lost a key, my room key. I went to house and I said, oh my God, I lost it. Am I going to keep searching around my house, or say, oh, I remember I left in my office? I would be driving very fast to my office. So driving fast is the simulation. And then when I come to my office, I start looking around carefully. That's the formal verification. And then when I realize, no, I was having lunch, I lost it there. Then I will be driving fast to my lunch place, and then I'll be looking it there carefully. So that's basically really layman terms, but in reality, you simulate the design. Let me see if I have a picture of that. No, you simulate the design, and then it executed one of the path. You ask yourself, is my solution or the assertion in that path? If not, I have so many other paths possible. Let me annotate here for a moment. So what you are going to do is, let's say these are the branches, control data flow graph branches. When you simulate randomly, let's say it simulated this path. So now you have you didn't find the assertion to be activated in that path. Now you have this branch or this branch. So which branch to select? Next time you want to apply constraint. Initial test could be random, you just ran. But next time you want to do something, so that if your heuristic said this path likely have, so next time you simulate, it's going to be one of those paths, and you slowly handle one path at a time. That's handles the state space explosion, and then that takes you to the particular point. Again, discussion on concolic testing is going to take too much time, and we can talk offline. But that's how you generate the directed test to activate the assertion. Writing manually and activating it is going to be nightmare. Now, this I briefly talked about. Should I, whatever assertion I use in pre-silicon, should I synthesize all of them as a post-silicon checker? Should I select some of them? And how do I select? Whom do I select? There is a lot of research from my group and many other groups. I can't afford everything. I can afford this much. Can you tell me which will maximize my security coverage during post-silicon execution or lifetime of the device? So I think this is a logical point. I'm going to stop here for 5 minutes. If any of you need to go to restroom, drink water, take break. So this is, let's say, no, not 5 minutes, 10 minutes. So this is roughly 35 in my one. So let's say 10 minutes break. But in the meantime, if any of you have any questions, feel free to ask me. So I'll start the discussion again in 37, 47, in 10 minutes.
Prabhat, I had a couple of questions.
Sure, go ahead.
So first thing is are there any languages or any frameworks that are suitable for security verification? For example, is SVA good? Say, system verilog assertion is it a good candidate to approach this type of formal verification methods?
So in the assertion-based verification domain, those are the only two one. Property specification language, PSL, and SVA actually supports PSL. There are many other languages, whether you go the SVA route or PSL route, it effectively enables you that space. You don't have to do any changes. If your simulator works on SVA, security verification will work. Only thing that's important then is really if you defined your threat model. Initially, when I covered this, you guys might have thought, why are we talking about it? That's the most important. Although I'm going to talk so many things, that's the most important bullet in all the discussion. Once you define your threat model correctly, then it boils down to converting that into a temporal logic and encode it as a SVA assertion. Rest is done.
Okay. So I was, so the following question is, I was looking into some documentation books and all. I actually even have your book, System Security.
Oh, so, thank you.
So I'm looking for some books or papers which can, it's a jungle, right? It's easy to get, it's very easy to get lost, and I'm kind of getting lost right now. So I was looking if there are any papers or books that you will suggest me, which will help me, gain a knowledge on how to do formal verification for security using SVA?
Right.
Not
So
now, maybe later you can let me know. Or
right.
I'll.
So I think if you want to do SVA, security assertion, I would ask you to start with the recent the paper. I may need to go to few more. So I don't want to go out of escape mode. So there is a paper on so you might want to not actually survey paper would be better. Any domain, this is not for security, any domain you want to start, start with a good survey paper. And I don't want to, because it's recorded, I don't want to officially endorse anything, but ACM Computing Survey or Proceedings of IEEE, they are like top tier survey from ACM and IEEE respectively. I'm not saying other publication venues are bad or anything, because they have a very high standard of review. So go for any of those. And because you talked about this one, would be a good starting point. But remember, this doesn't even touch security. This is only assertion based verification. But anything that has been told there, if you replace fault model or bug model by threat model, all of the arguments apply. None of the examples are security examples. This is only pure assertion based verification, but it does cover everything. How do you manually write assertion? How do you automatically generate assertion? Who is doing it? Where are the papers? Now that you have assertion, how do you generate test? Manually, automatically to activate these assertions? How do you talk about assertion coverage? How do you know you have written enough assertion? Do I need to write more? Can I write less? All of those fully covered, and as latest as 2022. The survey paper become irrelevant in, I don't know, 1, 2, 3, 4 years, because so much of information comes in. But you ask a bigger question. This question everybody faces when they're working in any domain. My always answer is go for a survey or tutorial paper. In top tier. Again, I prefer not to take any journal and conference names or venues, but you know which are the top tier places. Right? So go for those top tier places. Look for not a research article. Look for a survey article or a tutorial article saying like XYZ, a tutorial introduction. Those would be written, or magazine such as where is it? IEEE Spectrum, or what are the so something like I don't know. This is recognizing face. It's a serious problem. Communications of ACM. Any of the where articles comes from the general audience. That should be right starting point. If it is related to anything to do with security verification, feel free to email me. I always reply, unless there is a major submission or I'm flying, I always reply in 24 hours.
Great. Thank you so much.
You're welcome. Any other questions?
Yeah, I have also a question, not specific to security, but regarding tools. Are there any open source tools that we can use for these things?
Yes. So how do I say your name? Leonidas?
You can call me as you wish. I mean, Leonidas, Leo.
Leonidas. Okay. No, I'll try to say exactly the way. Leonidas.
I'm Greek, so my name is Leonidas, but it's difficult for most of the people. So when I'm speaking to English speakers, I say Leonidas.
Okay, Leonidas. Okay. So yes, there are a lot of tools actually, and whether some of the, because some of our work is already integrated in Synopsys tool, but I don't know whether they're selling it or is it part of the toolkit that they are going to sell in the next 4 or 5 years. For example, the FSM vulnerability mitigation, those have gone in there. It's part of a big DARPA project. I don't know, 50 million, 70 million, whatever big DARPA project. And so that's from the commercial side. From the
sorry to interrupt you. What was the name of that Synopsys tool?
Oh, I can't talk on behalf of them. All I can say, some of my research works has gone in there. I don't know whether they're going to release, whether they're supposed to be secret, but you will see that in commercial venue. And it's not just me working on those big DARPA projects. There are many people working, those are getting into the tools and stuff like that. And so And there are companies who are primarily focusing on security verification. Again, it's under recording, so I'm not going to take the names. If I take one name, other company will say, oh, we are also doing, you didn't say that. But in the public domain, you will find certain tool. Trust Hub, the tool site I said for threat models, there are some tools also. And another way I normally address this, sometimes it's very difficult to search the right word. Some groups put up their tools in GitHub like I do, but Google search might not find it. If you are interested in a specific problem or tool, send an email to specific researcher. Industry people, I don't know whether they want to, but in most academician, I can't talk about most, some professors like me, they would be happy to share their tool. But your expectation should be low. Those tools are going to fail on the drop of your hat. Whatever benchmark they said it works, it will work. Hopefully it will work. And then it might not work. So the classic example is my own PhD work. When I started assigned to my student, it stopped working. Because between then and when students started working, apparently C and C++, they came up with different standard. And there is a major standard change. You can't do hash include anymore. You have to do this and that. Anyway, so long story short, there are tools, not all of the tools, and sending email, and some of them put on. So for example, RTL fuzzer, that's also available, but you have to know what you are looking for. They don't call, I mean, that tool is not called testing for RTL security vulnerability or test generation. It's called fuzzing, F-U-Z-Z. And if you don't know that term, if you're not searching, you're not getting the right GitHub to download that tool. That's going to do fuzzing on RTL design to generate test pattern to check for security vulnerability. But if you send email to respective faculty member, then they point to you and there are tools. Not too many, but there are. So now it's time for me to start. Let's begin where we left. Let me go to let's go to the, so to recap where we were, we talked about why security verification is a challenge. We talked about the different threat model, metrics, and benchmark, and we spent some time on assertion-based validation. The remainder of this tutorial, I'm going to focus on some more ideas of simulation, especially security verification using machine learning. I'm going to talk about side analysis, and then I'm going to spend whatever time is left on formal verification. I'll try to focus more on machine learning and side channel, and then remaining time on formal methods. Again, those of you joined late, please feel free to stop whenever ask me to stop and ask me question as soon as you have a question. No need to raise hand, and there are only few people in the team. And feel free to turn on your camera if you feel comfortable. That makes me comfortable. It feels like we are sitting face to face and talking to each other. If you're not comfortable, you don't have to do it. Okay, so machine learning for verification. Before I go for security verification, what I'm going to do, so if you can raise hand or just turn on your camera or say it, how many of you are using machine learning actively some way or the other? You can click on reactions and press the raise hand button so that I kind of know where you are. Nobody's raising hand. Okay, that's fine. So machine learning, artificial intelligence, whatever it is, before I go there, let me talk about when you have a RTL design, gate level design, you can do static analysis. And static analysis, you can analyze control flow graph, data flow graph, concurrent finite state machine, all that stuff you can do. But the problem is, the problems are shown in red. It doesn't scale beyond small modules and needs a lot of space for doing this stuff. But if you want to do dynamic, only during simulation time, you are simulating and you are analyzing, for example, scalable, practical, but basically unless you simulate for a long time, you kind of don't know what is going to happen, how good your design is. Just because you didn't run a specific set of inputs, that doesn't mean no, you are fine, nothing happened. Now, of course, the third approach would be combining static and dynamic. It does take care of some of them, but it's still something remains. Interestingly, if you put Machine learning with static, specifically for security verification, it's an amazing combination. I'm not going to get into detail. I will actually show some very simple example to give you the scenario why that's the case. Even if you don't know machine learning, what is this engineer handcraft feature? Why is it scalable? What's going on? Where does it work? So first thumb rule, anytime you hear for machine learning, your idea should be somebody faking something, because machine learning does not work everywhere. It works in very few places, and there is a reason why it works and gives you 99%. And other places, you train with your design X, it might not work with your design Y. Of course, technology is moving like zero-shot learning, transfer learning, but in spite of all of that stuff, machine learning still have that problem. But some places it works like a charm. And let me talk you where they are. And security domain, it does. So we kind of, if you want to know more about machine learning and hardware vulnerability, this survey paper might be very helpful. This is very recent, as 2022. Now, what are the insight, key insight? That's what I'm trying to. So if machine learning algorithms, if you can guide it properly, it's actually would help you. So you are basically giving machine learning some domain knowledge to solve different problems. And since none of you raised hand, what machine learning essentially does, it basically kind of tries to find a line. Let's say all of the people in the room, we are taking temperature, and we are kind of figuring out who has fever, who has no fever. And let's say if I'm plotting, this is 98.4, the official fever demarcation. So if I'm plotting numbers for all of you right here, you guys don't have fever. If one of you, I plot a number here, then you have a fever. That's a classification problem. Machine learning tells you you have fever or not. You are saying, whoa, come on, I know it. You tell me your number, I'll tell you. Why do you need a machine learning tool? That's precisely the point. For such a simple scenario, you can. But let's say it's not a line, it's kind of a complex plane. It's not even a plane in a 2-dimension. It's a complex plane in n dimension. And then there are overlap and all that. For a human being, it becomes hard. But if there is a method in the madness, machine learning will figure it out if you're doing it right. That's the point. But anyway, I'm not endorsing machine learning or anybody. What I'm trying to tell you, where it works. And in security verification, how you can use it effectively. So how do you engineer all these and all that? But machine learning and verification, or security verification, how do they help each other? I'm going to show you a demonstration. Why? So what is a verification problem? So if machine learning you apply for verification, you can really generate assertions. You are guessing the agent from simulation data. Now, let me give you an illustration. What do you mean by you can generate assertion? If you are running your simulation for hours and hours and hours, and what you are observing is that whenever A is equal to 1, you are just observing B is equal to 1. So what is your intuition? All these behaviors you are observing, and you are observing anytime, any clock cycle I saw equal to 1, that basically means A implies B. But of course, you have to have a question mark. You still don't know. So that's how you mine traces to figure out, is there any functional B? Remember, I'm using machine learning because nobody is telling me what to do. If people are telling me these are the behavior you would be checking, I don't need machine learning. I want machine learning to figure out, in verification domain, we call them invariant. I want it to figure out what are the things for this design is golden, true, forever, eternity, God's words. What are those? I'm still putting question mark because I still have to formally validate that is true. But all I wanted to illustrate, you are simulating, you are observing, based on that, machine learning can figure out what are the relationship where it seems like strong correlation. Right now, so that's basically machine learning is doing. I'll just do animation. I won't give any more detail. Any of you have any question? And you can use machine learning for not just assertion generation, even for debugging, even for coverage closure, even for test generation. I'll show example where you are doing. So in many domain, you can do this stuff, and machine learning works like a charm. It basically works. It figures out certain features and it does wonderful job. Now, are they friendly or unfriendly to each other? Fundamentally, let me show you that. So, by the way, Ashraf, when you ask me about are there any books, no books will teach this stuff, because that you get of years of insight, and to give that insight you need to explain apples and oranges, and that's goes out of the context of that book. It's not that the writer doesn't want to give you that context, it's just, but anyway, in this context, so because the reason I'm explaining this context, when you want to say should I use machine learning in verification in this context, should I not, this insight will give you that value. What is this insight? So space exploration, both of them do it. How do they do it? So in case of simulation or verification, you have a variable state space. You have a huge simulation, formal, doesn't matter. You have a huge state space. In case of machine learning, you have a lot of feature space. What is a feature? Number of gates, number of inputs, number of fan in, fan out. Which feature is useful? That's I'm not talking about. There are so many possible features in a design. Like for human being, we say, oh, nose looks good, eyebrows are very good, and forehead is flat. Those are features. Does that mean that person is intelligent or not? That's a different story. Or always smiling, have a positive personality. Those are features. Is that good for as a perfect employee in the future? That's different. That's a different story. But it is a huge feature space. And how do they relate? In a variable state space, in the simulation, that's what you deal with. And in feature space, you really deal with data. Machine learning tool get a lot of data that could have been generated by simulation. May not be, it may come from somewhere else. But for every simulation is an instantiation of an n variable state space, n dimensional feature space. See, they're actually related. If you have a n bit states, so you have 2 to the power. If you encoded a state with n bits, that means you have 2 to the power n possible states. That means when you are simulating, you are really getting a tons of data. And the machine learning really have an n-dimensional feature space now. So what is n-dimensional feature space? Let me try to draw it for you. So let's say you are looking at only 2 features, number of gates and I don't know, number of gates greater than 2 inputs. And another feature could be number of gates better than 3 input, or let's talk about output fan out. Number of gates, again we are plotting these gates, and with the fan out, I'm just abbreviating, fan out greater than 3. Now, why this feature? Feature selection is a classical problem. I'm not going there. But based on this, you are going to plot the values differently. But this is a 2-dimensional feature space that machine learning has to find and in a 2-dimensional space, a cart is basically a line or kind of something. But if you have a 3D, 3 features you are thinking, can anybody tell me what's the cart on a 3-dimensional space? It's a 2D, it's a plane. If you have a 4D, a cart is going to be a 3D. So in layman terms, it's a bunch of equations that machine learning has to solve. Of course, I'm not talking about how do you solve it using neural network or decision tree or all that stuff. I'm going to skip all that details. But nonetheless, that's what they're dealing with. And verification is deductive. What do I mean by that? You have a model of the design, your specification, your RTL design, and you are trying to do simulation and you are trying to answer certain questions. Is traffic light controller going to become green at the same time, both sides? Is it true? Is it false? So whether it satisfies the model, that's what you are. So you have a specification. This is your implementation. You are simulating. You are trying to figure out, does this satisfy this model? I'm assuming model is golden. In case of machine learning, it's inductive. It's actually inverse. So you have a data. You have a data. You don't have the model. You are trying to figure out, does this data, you're trying to guess the underlying model. What is it trying to do? So they are actually friendly to each other if you can combine them right, if you hit the right nail. And they have exactly same problem. They are equally built. Why do I say that? In variable state space, it leads to state space explosion when you're doing formal verification. Number of states explode. In the feature space, same thing. cars of dimensionality. If you add more and more features, then you don't know how many features you want to use. If you use too less features, it might not make it good. If you add too many features, you won't be able to handle it. So that's basically the story. Any questions on? I actually did not say anything, but which I'm going to say now. How do I use it in a specific scenario? But I wanted to give you this 100,000 miles above bird's eye view. What's going on with how friendly or unfriendly they are together? Any of you have any question on machine learning and security verification? Now I'm going to go show you very sample examples of how do they look or what do they do. And this is basically, I think it's a public, and there are many work on this. I'm only citing my paper. A disclaimer: there are hundreds of other researchers brighter than me doing significantly better work than me. I have a choice of citing mine or theirs. I just decided to cite mine. But there are a lot of work on using vulnerability analysis using machine learning. And the survey I showed, the 2020 survey, that shows you hundreds, or I don't remember, 150 or 200 papers on that area. But nonetheless, what is it doing? So it gets a benchmark, gets different kind of parameters, and figures out, this is based on reinforcement learning, figure out a reward function and start with a random pattern, start flipping bits to maximize the chances of activating the trigger of the Trojan. That's the goal. Machine learning is telling you which bits of the input to flip. Now, if you want to break it down to layman terms, what's going on? Can anybody spell it out in layman terms? Why flipping this bit versus that bit? I still have 2 to the power n bit combination if you have n bits. Why would it help? What is machine learning figuring it out? Why am I, if I talk to you 10 minutes, what did I learn and decided to hire you? 5 minutes, half an hour, whatever. What did I learn? What did machine learning learn here or can learn? What do you think? Okay, what it learns is that you may have n inputs. Let's just say 64 input. If you don't learn anything, you have to try 2 to the power 64 combinations or attempt to try. But if you learn, certain signals actually have a correlation, certain inputs have correlation with the rare part of the node. Remember, our goal is the rareness. If you don't have any assumption, then you can't do anything. So I want to activate the signals in the rare area as much as possible. If I can figure out, I think this input has a correlation, that input has a correlation, and these two inputs together, individually, they are not helping. Together has a correlation. Then I reduced my state space from 2 to the power 64 to 2 to the power 4. That's the catch. Can machine learning find, and we call it affinity. Let me write it. Input affinity. AFFINITY. So there is no magic here, and machine learning works here. If there is a correlation, machine learning will find it out. If there is no correlation, it will not find it out. As a human, if you could have figured it out, wonderful. Then you don't have to try to the 64. You could have tried. Remember, there is still not 100% guarantee. Instead of randomly flipping bits, it's telling you which bits have higher likelihood of hitting the target by flipping those bits, by trying those test pattern. Or you tried this one, which should be the next one to maximize switching, you try that one. And these kind of problems have been well studied. If you come from a power domain, power virus, many years ago, a lot of people did work, including me. Can I give you only a pair of test cases? That would tell you the maximum switching in the circuit, so that you can design your cooling mechanism and all that stuff. This is analogous to that. So many of the techniques you are seeing here or tools you are seeing here, that is nothing novel, nothing new. It's recycling of the ideas from other domains applying to the security domain. So the way I'm trying to present this tutorial, whatever you know in the verification domain or other domain, you can simply apply it here. So this is one example. And then let's go for next example. So malware detection you talked about, so I quickly punched in. So when you want to do malware detection using hardware performance counter, remember each hardware performance counter for the machine learning is a feature. So, and then when you want to train the machine learning model with different hardware performance counter, there has to be intuition. Why? If the branch misprediction rate goes up, there has to be intuition. Okay, that machine learning tool will figure out when malware is running. So you have to train with a set of malwares, and then you have to test with other malwares that it hasn't seen or with the different context, and you see whether machine learning detects it. I wanted to show you, and same thing you can do with embedded trace buffer. The trace buffer I talked about, and you can read some of the recent works. And by the way, most of the work I'm citing here are the recent works, but there are a lot of early works on those. Now, I want to highlight something else. Polymorphic, one of you mentioned about, and I want to introduce polymorphism. Spectre and Meltdown, all of you know, and there are so many detection techniques, so much of mitigation. If you use a Linux machine, if you do CPU/proc info, it will actually list you the processor you are using in your laptop or computer, what kind of attacks are possible, what patch is there, whether you install the patch, what it is defended against, what it is still vulnerable. You can do it right now. You can look at it. I'm sure in Windows systems there is a way to figure it out also for processor, how much known vulnerability, which are patched already, which are not patched. Spectre Meltdown, it will swap. Spectre 1, 2, 3, patched, defended on this day, this patch defend against this and all that. So what I wanted to show you, if you are running, these are the features: branch miss rate, lower level cache misses, lower level cache references. So it's a 3-dimensional story. So what machine learning figured out, based on the plot, the normal behavior tends to be here, and the malicious behavior tends to be here. As you can see, there is may not be a straight line, but there is a kind of clean clustering between them. Machine learning would be easy to detect. But when attacker figure out this is what machine learning did, they kind of did polymorphic stuff. Because if you know, if the attacker knows these are the feature you are using, they will add junk instructions in the malware. That's not typical malware functionality, just to obfuscate this behavior. How would that look? It would look like this. Evasive malware today would look like this. Those green dots, they are like all over the place. And there are detection techniques, and that I'm showing it here. That's also a 2022 recent work. But I'm saying that's what polymorphism does. It enables you to what do I call, bypass known detection techniques. I saw a hand, Praveen. Do you have a question?
Yes, sir.
Go ahead, please.
Actually, when we say context-aware security mechanisms, so can these performance counter and whatever we are seeing right now with machine learning, can we call these mechanisms as context-aware?
Yeah, absolutely, absolutely. Look, this is not a machine learning thing. One of you asked me, I put something quickly, but dynamically I controlled it. But in malware domain, we need to answer that question. I need to go back in time, and I have to tell you how malware detection happens today in your computer when you install any antivirus tool. Antivirus tool looks for a signature, static signature. It doesn't run even malware. Think of an equation. It computes an equation and figure out what it is. And it's very easy to bypass that signature. And that's where this the obfuscation and ETB and HPC based things, those are not implemented. Any tool you are running now, they are not. This is a research area. This is known as hardware assisted malware detection. This is an active research area. You can see here, or I don't know whether malware detection, I had a paper showed up, but these are active research area. Yeah, so hardware assisted malware detection. These are active research area, and where you trace hardware performance counter and so on and so forth. And this has a much better chance of, even then people can do obfuscation, polymorphism, and try to bypass it. Or what I'm saying is, if you do simple antivirus, it's not going to work. You do hardware assisted detection. Even hardware assisted detection, an attacker can bypass by doing polymorphism. Then I say you can do something else, which I briefly talk about. I'm going to skip quickly. You can do explainable AI, like model distillation or Shapley values, and then you kind of figure out inherently. So what is the basic idea? If you made a mistake in life, if I made a mistake, my parents will tell you, son, don't do this, because I did this in my childhood and this happened, that happened. So you learn from mistakes. Now, if you are intelligent, you learn from others' mistake. If you are dumb, you are not going to make all the mistakes in your life on your own. Here also same thing. You make a mistake, misprediction, and you want to feed that to the input. What explainable AI does, it tells you why you made the mistake, what feature actually contributed to the mistake, and you will do a better job correcting it. And it is improving process. There are also many other techniques. This is not a machine learning tutorial, like ensemble boosting. You use lot of weak classifiers, and second one is fixing the error of the first one, or the accuracy of the first one. Third one is fixing the problem of second one, and it's kind of ensemble of a lot of algorithms together. So there are more of those. They take care of polymorphism, and I'm going to skip all of them. Unless somebody has a quick question, I'm going to go to side channel analysis. Praveen, one quick question, because I don't want to do machine learning here.
Yes, it's not regarding machine learning. I want to ask, like, apart from hardware performance counters, what other parameters we can consider for as a data?
Right. So lot of things you can consider anything as data. Remember, after all, it's a feature. What machine learning will work. What people have done, have seen and published is the three things mostly: hardware performance counter, embedded trace buffer, trace data, and electromagnetic emanation data. Any kind of side channel data. People are using them to kind of guide the detection or help in detection. Now, even each of them can be further zoomed in. When I say trace buffer data, why can't I dump my cache data? It might take time. It might not be real-time detection. If it's a ransomware attack, if you take too much time to dump your cache data, by the time you kind of say, oh, it's a ransomware, most your files are encrypted already. It's too late. If you do it too early, then it could be false positive. So that's why I said we can talk offline, but this discussion will devolve into something not hardware security verification. Okay, let's move into logic testing versus side channel analysis. So what am I trying to tell you now? I'm going to tell you, can I generate tests to detect, let's say, hardware Trojan or any vulnerability? Earlier I talked about assertions, and this is about tests. Can anybody tell me what's the fundamental similarity or difference between test and an assertion? An assertion is a property. Are they cousin brother, cousin sister? They are distant people. Test and assertion. Assertion or property can cover all possible scenario. Test only cover the scenario or checks the scenario at that specific time. You can visualize, let me annotate here. You can visualize, if I draw a line, if this is the assertion or property, a test would be a tiny dot somewhere. Property or formal verification guarantees completely. Assertion guarantees based on whatever you ran so far. Test only guarantees. So if you want to talk about in terms of strength, test is really the weakest. Assertion is stronger, and property or formal verification in the context of property, and assertion in the context of simulation. That's basically strength level. If you could do property checking, formal verification, do that. If you cannot do it, go for it. If you can't even do that, then go for this. Right? Any questions? Okay. Now, moving forward. So for the logic testing, you are doing always simulation based validation, right? What are you doing? You are doing test generation, running the test, coverage, and all that stuff you are doing. Even if you do all of that, you might get a 90% coverage of whatever your metric is. In our case, it's a trust metric. But there are certain tests not covered. If you keep running random again and again, what is going to happen? It's not going to go to B. A is a start state, let's say. And you know B is not covered. In general, when you say I covered 95%, the remaining 5% could be millions of scenarios in a design. Or you can say, I know where I am. I know where I want to go. Why don't I manually write a test to do that? Actually, many people do that. Manually write the test. But in large design, it's kind of close to impossible. And we kind of illustrated that in a cache coherence protocol verification story. Why, no matter what you try, it's not going to work. How is it people automating it? So idea is simple, although I didn't cover formal verification. Model checker is one of the formal verification tool, and you can download from open source. And I'm showing an example of how it's used. So let's say you want to generate a test, you have a processor design. You want to generate a test to stall the decode unit of the processor unit. You want to write, you dig the design, you write a property that say exactly the opposite of what you want. Your decode has a stall bit, you say stall bit cannot be 1. And you give it to the model checker. Model checker comes up with a counter example. That's your test to activate, to make the decode stalled. This will work for any design. But only problem is, so this is exactly what it's giving. You give the design, give the negation of the behavior you want to test, you will get the test. So this very simple idea, and this existed forever. My first patent was this idea. But this, whatever model checker does, that existed. I just took that idea, applied to the test generation problem for processor verification. But anyway, so this is still a model checker. It's still a formal verification tool, and it's still going to have a state space explosion. So then basically, can I reduce the complexity? There is a tons of work in the last 15-20 years. Many of them are from my group, and I'm going to skip all of them. But what does work, and all of them has problem, concolic testing, which I introduced in the context of assertion activation. Now I'm introducing it again. It's the same thing, same concolic testing, by the way. And how does it work? Let's say you decided this is the instruction you want to activate, or this is the branch, this is the rarest branch. That's where you think Trojan is hiding. You want to activate it. How do you do it? You simulate and you get bunch of traces, and then you find the constraints and you do the constraint solver, and you ask yourself, did I get the test or I need to repeat the process again? That's basically the concolic testing story. You can do that, and you can do that for Trojan activation. But what's the catch? How is it different? Catch is, Trojan activation problem boils down to rare branch coverage problem. Because your assumption is, if anybody wants to hide a Trojan in RTL design, it's going to hide under rare of the rarest branches, the branches that are not covered under normal execution. That's what your problem. Then you can apply concolic testing. Then your normal testing story becomes a security verification story, because that's your threat model, that's your assumption. Now, how do I do, let's say, hardware Trojan detection? If I'm not going by the branch, you can do many other techniques. And I'm going to talk about only 2 techniques here, just very briefly, so that you get an idea what is out there. You can download or read. So basically, first you take a design, do the rareness analysis, figure out which signal or variable is rare, which is not rare, based on certain threshold. Then you have a list of signals and you are kind of generating test. So the idea of the statistical test generation, let me go straight to the idea of the statistical test generation. This work started in 2009. Idea is that if you know what are the rare nets, and if you believe attacker is going to use those rare nodes, you want to activate or flip those nodes as much as possible. So you want to come up with an input pattern such that these nodes are getting activated a lot of times. And what is the analogy? Let's say this is a room. In this room, there is a dirt board, and there is a point where you want to throw and hit the dot. And you are blindfolded, but you know which direction this is. Are you going to throw your dirt this direction, that direction, or that direction? No, you should not. If you know it's in the middle of the thing, you should not also try to throw here and here. You should try to throw all your dirt in this direction to increase the likelihood of hitting the dot. Now, of course, in this case, you do not know whether Trojan is constructed using this AND gate or that. You don't know a lot of stuff, but you are increasing the statistical likelihood of activating the Trojan if there is a Trojan. You don't even know if there is a Trojan. That's the whole idea of statistical test generation. And again, there are a lot of work in this from 2009 to now. I'm guessing like hundreds of 200s of publication in that area. And it's basically you try to flip. You start with some pattern, you try to flip a bit or two and see what's going on. Am I activating a lot more normal nodes or a lot more Trojan nodes? And then you keep some of them, and then you kind of ignore some of them. That's basically you do. And then that's one way of doing it. And I'll tell you another extreme. So before I talk about the extreme, what did I talk now? You have a large design, but I identified few rare nodes. Typically, there could be thousands of rare nodes, by the way. I am drawing only 3 of them, or let's say 4 of them. Let me draw a little bigger, clear. Let's say this is your design and you have 4 rare nodes. What statistical approach tries to do, I want to generate tests so that I activate some of these rare nodes n number of times so that I maximize the probability of the trigger getting activated. The opposite extreme is tarmac, which I'm going to show in a moment. What it does, it basically says, you know what, why am I trying to activate each of them n times? That's a statistical theory called n-detect. Why am I trying to activate why am I trying to activate each of them n times? Why not try to activate all of them using single test? Because if I can do that, then I don't care whether the attacker is using 2 of them as a trigger, 3 of them as a trigger, 4 of them as trigger. I have a single test that would activate all of them. And if there is a Trojan, I'll find it. And that's the whole idea. Try to activate, statistical says try to activate one at a time. And this one says activate all of them. But you and I realize the functionality of the design may not have a scenario or input, all of them being true at the same time. And remember, the true means this variable is 1, that might be the rare condition. This variable may be 0, and so on and so forth. So then what is the next problem? Okay, if I can't activate all 4 of them at the same time, what about the maximal click? What about 3 of them? Let me use a different color. What about these 3? What about another color? What about those 3? And so on and so forth. So this is a maximal click. So my goal is to generate minimal number of tests to activate the maximal click. But again, there are many research problems as of today. If you want to solve, the number of potential clicks are exponential. Which clicks you want to start with? How do you do click sampling? If you do random sampling, all the all the guarantees are outside the door. And then how do you do test generation? That you have to do a satisfiability problem. If you have too many nodes in the satisfiability graph, and I didn't cover satisfiability yet, SAT solver, that might choke. How do you make SAT solver scalable for this problem? So there are many such research problems people solved. There are many such problems not solved yet. But nonetheless, this is the maximal click. If you want to read this work, this is a 1-year-old story. How do maximal click sampling, which is, so again, as I said, if you have multiple nodes, you are trying to activate. And in this particular design, what are the exact test pattern that would activate those clicks? In this case, we need only 3 tests. If all 4 nodes were satisfiable at the same time, I needed exactly 1 test that is guaranteed to detect any Trojans that's possible in the design. Although number of Trojans are exponential, number of inputs are exponential, that's a cute solution to solve that problem. Now, anybody has a question on Trojan detection using logic testing? Because I'm going to talk about what's wrong with it. So positive side is tiny or non-tiny, you can detect it. Negative side is the test vector space is huge, whether test vector, whether it's the number of clicks, and large Trojan meaning if you have an AND gate with too many inputs, then probability of activating it goes lower. Side channel analysis doesn't care about inputs. The good part is large. If it's large, it's actually better. It's going to leak a lot of information. It's going to consume a lot of area. It's going to introduce a lot of delay. So that's much easier to do. But what is negative? Negative is, think of a 1,000,000 gate design, and your Trojan is only 2 or 3 extra gates. So then how do you figure out? Let me annotate it here. So if you have a large design with order of millions of gates, and you kind of have 3 gates somewhere and you don't know where they are, the kind of difference, even if you are measuring the kind of side channel, let's say you are measuring power, the difference in power because of these 3 gates would be, you won't be able to detect using $30,000 oscilloscope. because that difference would be that tiny. That's one point. Second is, forget about Trojan. There is no Trojan. Run this design twice. The difference would be in the order of 2 to 3%, can be up to that much because of noise variation and process, all that stuff. And these 3 gates is going to hide in 0.001% margin. You don't need even 1% thing. So the noise or process variation is going to hide all this stuff. What do you do? What do you do? So there are few solutions. What I wanted to show, I will show you through animation. So this is the work that it basically, it's in CCS. We worked long time. We basically said, we observed something very, very simple. It's not that in this table I plotted this. Whatever is negative for this, that's the positive for this. Whatever is positive for this is actually negative for this. We say, oh, these two, logic testing and side chain analysis, complement each other very nicely. So before I show that, let me show you an animation. In logic testing, you apply a input. How we get it, we talked about a little bit. Let's ignore that for a moment. We compare the output. Assuming this is a Trojan, which is based on functional output. Now, of course, we know the problem is the number of possible test patterns are too much and it's going to hide in rare and it's a problem. Side channel input is not that much important. You can apply whatever you want. We are going to compare, in this case, I'm talking about current or power or path delay, whatever we are going to compare some side channel signature. I don't have to activate the trigger. Even if few gates out of the Trojan, they are working, then they are going to deal side channel. But the problem is the difference of this side channel would be so minimal, it's not detectable by any mechanism because of variation. So then what can we do? Before I tell you the idea, let me again give you a layman story. Let's say you are flying a plane and you want to land in Gainesville, Florida. That's where I am. And you don't know where Gainesville, Florida is in Florida. Let's say for a moment, Florida governor decided to turn off lights in whole state and turn on the light in Gainesville. It would be so much easier for you to land. Suddenly, it's easy for you to locate the airport. Same idea. What we want to do is we want to apply tests such that, remember, this is also based on threat model. If your threat model is wrong, everything goes down the drain. If you know this is a suspicious area where rare nodes are, again, remember, it may not be contiguous. It would be this, and this. My goal is to generate test pattern that would maximize switching here, maximize switching in these suspicious nodes, and minimize, again, minimize also have a M, so I'm going to say N everywhere else. Minimize the switching in rest of the design. Ideally, what I want to do, I want to apply input such that these gates start switching. Everybody else is not switching at all. You can't do that. You can't percolate input changes without changing. So that you want to minimize everywhere else and maximize here. That's the goal. If I can do that, then the kind of difference would be suddenly visible if there is a difference because of the logic in these areas. Any questions? So we are combining the advantage of logic testing and advantage of side channel analysis together using maximization, minimization problem. Any questions? Okay. So again, this work appeared in the 2-year again IEEE transactions on information and forensic security. And let me show you a animation of how it's supposed to look. Let's say you first of all, you don't know where the Trojan is or whether there is a Trojan, but you basically, let's assume I am telling you these two rare nodes, if they activated at the same time, Trojan would be activated. And you will be able to see the difference of the functional output. So then the input pattern should be able to activate this. Let's say I run some input pattern. Luckily, in this case, these two nodes are getting activated at the same time, but so does other nodes. The blue ones are regular one, non-rare one. So that means it's creating some difference in the power or current or whatever, but they are also contributing so much. So if you kind of plot, sure, if you are plotting your the difference switch, which is this one, this goes up, that's nice. But what also goes up, the overall switching. But you say, well, they are still good. No. This one is a total switch in a different scale. It's like order of magnitude more. So this difference of going up, you will not be able to detect at all. But if we apply what we just talked about, and where you kind of get the target hit and very minimum number of other nodes switching, then you will be able to have this effect. In the suspicious area, those switchings difference is going up, but overall switching is going down. Then that's a window of opportunity. Don't worry about these variables and symbols and all that. We can read the paper. That's a window of opportunity of detecting. So what I just demonstrated is sensitivity is the main problem in side channel analysis. Trojan or any security thing, they are so tiny. Even if you measure the area, you won't be able to figure it out. Power, anything, you won't be able to figure out unless you somehow do something to improve the sensitivity. So although it's a verification problem, but you have to do something to be able to verify. Otherwise, you won't be able to detect it. So what I talked about, you have to also take care of few other stuff in many different scenarios. Any questions so far? Okay, now we have roughly 30 minutes to talk about formal verification. So raise of hand, show me how many of you know formal verification. Then I can skip up of the or worked or use something. You use property checker, equivalence checker, SAT solver, theorem prover. If none of the words sounds familiar, okay, so one hand, let me just do a little bit of basics and then I go in. So there are a lot of formal verification method. I'm only going to talk about 3, not necessarily these 3 are most important, but I'm going to talk about to highlight how in the security context people can use it. I'm not going to spend time how in the formal verification domain, functional verification people are using today. So there are many formal verification technique. It's not a laundry list, but this kind of covers most important one. Theorem proving, you prove a theorem about systems correctness. Property or model checking, this is most widely used. Those of you know, few years ago, the Turing Award went to the people who invented model checking. Turing Award is kind of Nobel Prize in computer science. And then equivalence checking is used in a specific context when you have a RTL design, and that's kind of golden, and you spend 6 months verifying it. Now you synthesize to get, you don't want to do 6 months of verification again on the get level design. You do equivalence checking. Now, only odd man out is symbolic simulation. It has a word of simulation. It also has a word of symbolic. So it's actually combines the best of both worlds. In simulation domain, you need 2 to the power n inputs. In symbolic simulation, you need only 1 input. So you actually still simulate, but you symbolically simulate. So it's actually a bridge between formal verification and simulation based verification, but I decided to put it into this category if there is no third category for it. So what is model checking or property checking? You have your specification is actually the property here. You designed a traffic light controller, you want to write a property, both sides of the traffic light controller should not be true green at the same time. You write it, give it to the model, you get 2 answers. Unless it leads to state space explosion, either you get an answer, yes, you are right, the property is satisfied, they will not be green ever in the lifetime of the traffic light controller, or it will tell me, no. It is, here is a scenario where both sides can become green, and it gives you a counter example. If you remember, I am playing with this counter example and convert into a test generation story. And that was the patent I was referring to. But nonetheless, property checking is the most widely used formal verification technique today in functional verification domain as well as security verification domain. You can use exact same framework, only difference is specifying these properties. That's it. That's the only difference. Once you have your threat model, manually or automatically, you can generate the properties. Remember, assertions are same as properties. If you apply them in a formal verification tool, you write in temporal logic in property form, property specification form, or if you're running it in a SVA or any Verilog description, you write it as a sentence in the simulation. So same property you can use for assertion based validation, unless you can completely verify it, or for property checking, or both. Any of you have been questioned? Lot of the work in verification you can reuse between functional verification and security verification, between assertion based validation and formal verification, and this is one of them. And I think this is the most important one, writing properties. And they are all in temporal logic, whether in assertion, whether property, they are in temporal logic. Any questions on this? And more, by the way, model checking is a full semester course in University of Texas at Austin. I'm covering it in a single slide. Either I'm very good or I have done a very bad job here. Okay, let's move on. So this I already talked about. If yes, if no, I'm not. And this is the Turing Award I was talking about in 2007. And going back to some of the examples you already know, I keep talking about temporal logic. E is basically a one scenario I want to test. A is always all possible scenario, and G you are kind of looking at that. So no matter what it is, even if you ignore all these, for example, if I want to do mutual exclusion, you are saying this scenario and this scenario should not be true at the same time, and I want it to hold for eternity. You start with a finite state machine, keep expanding it clock cycle by clock cycle. Think of you are holding a torch and you are checking, is it true, is it true, is it true, and walking through that states, unrolling the state space clock cycle by clock cycle and checking the story. And that's when state space explosion happen, unless you kind of know abstraction and all these techniques which I'm not talking. And and basically some of the things, for example, you apply A and B, and if it's an adder, you want to check if the result is equal to A plus B after 4 clock cycle. So you can write different things, different checks. And non-starvation basically mean if somebody requests, eventually they will get a acknowledgement. If a car is waiting in a traffic light controller, it would eventually get a green signal. That's a non-starvation property. So you need to define what behavior is interest to you, and you kind of then write it. And when I talk about assertion-based validation, in the security context, I showed how they would exactly look like. So I just created a table to tell you this is a safety scenario, this is a liveness, this is universal, this is existential. This has to be always true. Even if one time it's true, I'm okay. Safety basically means so liveness basically means something good will eventually happen. For eternity, you want to look at it. Safety basically means something good will always happen. Safety is nothing bad is going to happen in the near future, in next 10 clock cycle. If a car is waiting, within 5 or 10 times step or second, it's going to get a green light. That's kind of safety. Liveness is it will never become green both sides at the same time. You have to check for eternity. This is much harder to model, much harder to check. This is easier to model. Most of the time, anybody saying I'm doing property checking and whatever, they're actually talking about safety checking, safety behaviors. And the main limitation is state space explosion. So, and then because it uses binary decision diagram, I'm not going to get into detail. And then the BDD decision search tree, I'm going to skip all that. Otherwise, I might not have time. And then there is by the way, this is one of the most cited paper. This slide is in computer science, which basically said binary decision diagram may have subgraphs, they look similar, and can I point to that subgraph directly? So for example, the left hand side of B and this side and here is the same subgraph. C01, C01 looks same. And can I point? This is known as reduced order binary decision diagram. This is by Randy Bryant. Of course, it has to still prove this as a canonical property, but no matter what it is, that simple idea revolutionized verification domain. Otherwise, we'll be able to do using simple BDD only a design of 100 gates. That's it. It's a toy example we could do. Now we can go for thousands, and if you do right abstraction, you can go 10, 20,000 without getting into state space explosion. It's still not there in millions and billions, but it's still a useful story. If BDD also fail, you can go for Boolean satisfiability. Boolean satisfiability basically means if I give you an equation, can you find out assignments to those variables so that that equation become true? given any design, if you remember, any design or any combinational logic can be expressed as sum or product of sums from. This is actually a product of sum form. So then Boolean satisfiability problem is, can I make this true, and all the other multiplying factor true, and without getting a conflict. So for example, to make this one true, I may have to do x1 equal to 1. To make this one true, I may have to do x1 equal to 0. You cannot make x1 0 and 1 at the same time. Thankfully, there are other possible solutions. So you need to look for. So that's what SAT solver does it for you. Now, SAT solver theoretically is a NP hard problem if you know complexity in computer science. But practically, because the way we write design, there is so much of redundancy. There are so many ways of solving SAT problems today. Engineering a SAT solver, starting with a PhD dissertation in Princeton. Now, even although theoretically it's supposed to fail after like 10, 20 variables, even for thousands or millions of variable design, you would be able to do SAT solving. And that's why many model checker actually use a SAT solver in the back end. They convert the design into this kind of conjunctive normal form, and then they apply the property. Now the catch is, okay, in combinational logic, I understand it. In sequential logic, what happens? You unroll the design. You kind of guess within 20 clock cycle, I think either it will fail or we don't care. Unroll the design for 20 clock cycle. Then it's a fully combinational circuit. Convert it into conjunctive normal form, then apply a SAT solver. You don't need to understand these basics of satisfiability from unless you want to work in a core SAT area. All you need to understand, SAT solver is a publicly available domain. Property you can write, put the design property, converting to conjunctive normal form. That's also tools exist. So you just call different tools in your methodology. That's it. That's all I'm trying to convey here. Any questions? You need to call a design tool that would take Verilog design, generate conjunctive normal form. You need to call another tool, SAT solver or SMT solver, that would solve that for you. And either it will tell you, yeah, your property is true, or nope, your property is false. So I'm going to skip all these conjunctive normal for satisfiability and all that, but this is what I just summarized. You get your net list, you get your design constraints or your properties, you put them and give it to a SAT solver. You want to run one property, give one property. You want to run a lot of properties together, you can do that. You can use SAT solver even for equivalence checking. How? Why? Give the original design, let's say RTL design, give the gate level design, put an XOR gate at the output of them, and give the whole thing to a SAT solver, all of it. What does SAT solver do? The output, it tried to make it 1. If SAT solver is successful making it 1, what does it mean? When does output of an XOR gate becomes 1? When the inputs are different. If SAT solver is successful and say it's satisfiable, that basically means these two designs are not equivalent. If it says it's not satisfiable, then these two designs are equivalent. So SAT solver is a powerful tool for do property checking, for to doing even equivalence checking. And these are the theory and all that. Let me show you how property checking is done in a SAT solver. So basically all you do, you start with initial state, and these are the transition relations. So in layman terms, all of these is actually your design unrolled for k cycles. This is your design. Forget about the equation and don't curse me. I didn't come up with this equation. And then whatever property you want to check, you give the negation of it. And then all of these becomes a conflict clauses, give it to SAT solver, and that's a property checking. So that's basically model checking using SAT solver. Theoretically, that's what it is. Now, I just gave you a background, and now I'm going to, with those background of formal methods, I introduced all the topics, whether you realized it or not. SAT solver, model checker, equivalence checker. Now I want to apply them for security verification, and I'll make it very quick. This is a simple example. What I want to demonstrate here, this is an embedded system, tiny embedded system, tiniest, which run two tasks or two programs, task 1 and task 2. Program 1, it can run in 0.5 volt or 0.9 volt. Program 2 also you can run at 0.5, 0.9. The numbers you see in the edges, it says if you are running task 1 in 0.5 volt is going to consume this much of time and this much of energy. For everybody, that's the path. And given an energy and timing constraint, in this example, this is the only valid path. Only valid path. Any other path it executes that violates the design constraints. If you know real-time systems like airplane, the landing gear has to be engaged by 20 milliseconds. That is a deadly constraint. If it doesn't engage, it's going to be a nosedive accident. So if an attacker wants to attack, it doesn't have to do Trojan here. All it has to do is make sure that the dynamic power management technique make a mistake, and instead of executing 0.5 volt, it executes 0.9 volt, so that it takes this path. Either this or this, doesn't matter. Both will violate the real-time constraint. And many safety critical hard real-time system, if you violate the real-time constraint, it's a catastrophic consequence. Somebody is going to die, whether it's an operating room, whether it's an airplane. So for attacker, that's the property you want to check. How do I do that? So this is a very long old work, but basically the reason I wanted to illustrate, all along I was talking about functional, non-functional, but even timing violation could be a serious security violation. Attacker can attack that. How do we do it? So Upol is a model checker from University of Sweden, and it's basically you can model properties, timing budget, energy budget, and all that. You can model properties. So basically it allows you to model everything in addition to time in the property, and then you kind of check it, and if based on that you kind of get the result. And if it satisfies, great. If it doesn't satisfy, you redesign it. The design has vulnerability. This basically I already talked about. I'm going to skip FSM vulnerability, what assertion or property you can write and check. Then equivalence checking to identify threat. This I talked about. You can give it to a SAT solver. But if you are thinking of, by the way, industry today uses this exact tool. Synopsys has formality, many company, Cadence has conformal, many companies has their formal tool. They are all wonderful under one assumption. These two designs are not drastically different. So that means if you are thinking of a processor, fetch and decode, they have boundary. They are not optimized across boundary. If you do that, then finite state machines are drastically different. All formal methods will fail. And then what can you do? You can map the problem to other domain. And there are some interesting works, including my group. When you cannot solve the problem in Boolean domain, you can map it to, it's called Grabner basis reduction, but ignore all these garbage. This is basically solving the problem in decimal domain. Convert design and specific implementation and specification to polynomials, and perform the polynomial division, which is nothing but subtraction. You keep subtracting the polynomial until it becomes a zero polynomial. And if it becomes zero, then you know they are equivalent. And if this is not zero, why am I saying this? Try applying existing formal verification technique, even for a multiplier. Forget about large design. A 256-bit multiplier, it will choke. Because of 2 to the power 256, it's going to choke. But these methods will work. So if remainder is not zero, that's also even good. Let me illustrate that point to you. Let's say it came up with a remainder A or B. So any assignment to these variables that makes it a non-zero, that's a valid test case to activate the vulnerability in the design. Take a moment and think about it. You did not know that if your design has a bug, you did not know if your design has a Trojan. Having a remainder not zero, it basically says, but again, this requires golden model. That's the only negative of this work. You need to have an RTL model or something golden you need to have. If you don't, then you can't apply this. So a remainder, so once you have a remainder, so this case, what are the values I have? If it's A or B, 1, 0 is a possible solution, 0, 1 is a possible solution, 1, 1 is a possible test. Under all of these three tests, you are guaranteed to activate the scenario. Right? Now, A and B are internal variable. So to create A0, you still need to figure out how do I make A equal to 1? What are the input combination? You still have to do that. But once you do that, here is the beauty. And beauty is if this is your design, you run one input and you are activating it, it actually covered a cone. You run another test, it activated another cone. So the intersection of these cone is actually your vulnerability is. You can localize that vulnerability. And actually in arithmetic circuits, we have shown you can actually eliminate the vulnerability automatically. I'm not going to go through all those stuff. I'm going to skip it in the interest of time. And just as a fun note, and NOT gate in the polynomial domain is 1 minus a. In the decimal domain, it's 1 minus a. And you do the math, you'll figure out why it is. 1 minus, if the input is 0, 1 minus 0 is 1. If input is 1, 1 minus 1 is 0. So output is matching. Same thing for AND or, and it's kind of little convoluted, but there is a beautiful relationship between input and output in decimal domain. And it would produce Boolean output though. And if you have a correct design, non-correct, I'm going to skip all that. Now I'm going to talk about theorem proving. In the theorem proving, again, I'm not going to go through this silly example. I give you certain rules. Who is mother of whom, who is father of him. I'm giving some facts. By giving name, I'm saying this is male or female. Now I'm asking you, is Bill a John of the uncle? Now a theorem prover will be able to take this information and tell you that. Now, in our case, what is to do with uncle and auntie and all that? It has to do with, given a specification, you will be able to derive these pieces of information. That's the golden unknown. Like the commutative rule in case of addition. We know that exists. Now I give you an implementation and ask a question. Let's say I give you a pipeline processor and ask you a question. Can you prove it's an in-order, it always performs in-order execution? Writing that as a theorem, and that's how theorem would look like, is the hard problem. Once you are able to do, then it derives rules from specification, state the theorem, and prove the theorem. There are automated theorem prover today that you can run, and it's going to do it for you. And then what that relates to us, and similarly, that's in the those of you come from the software domain, there is a similar concept called proof carrying code. So if I don't trust your compiler, I just don't need only binary from you. I also need a proof. Now you might say, wait a minute, if I hacked your binary, can I hack your proof so that this matching matches? No, mathematically it's impossible, and there are many ways of bypassing it. Same thing we have did for proof carrying hardware. When you are passing hardware, different companies are saying, oh, here is the processor, take it. Here is the memory, take it. I also want the proof that this design is correct. And how do I do that and prove validation? There is a mechanism to do it, and we have showed it works. And actually we showed how they can actually work together, because theorem proving is actually very scalable. But writing theorem, and when you run a theorem prover, the system will fail. Fixing it, that's a hard problem. So therefore, what we tried to do, can we do model checking on a module level and get the constraints, and do the theorem proving at the system level, so that I have to run less theorems and I have to just help the theorem prover less. But again, you can go through these works, and I'm in a conclusion slide. So basically, to conclude hardware security verification, I want to tell you this security problem is a cat and mouse game. If you do not define the threat model correctly, your verification techniques are not going to work. Even if you define your attack goal and you kind of know what attack happening, and then you build the countermeasure, and you still have to verify the countermeasure is working correctly. The attacker is going to then fix or improve the or bypass. We talked about polymorphic story and all that, and then we'll come up with a stronger attack, and then you have to come up with stronger countermeasure, and that story will continue. So that, I believe, brings me to the end, and we have about 10 minutes for you to ask any questions. And if you have questions after the tutorial, you want to send me an email, you can expect response from me in 24 hours, unless I'm flying or very specific situations. So any of you have any questions?
Yeah, I have a similar question to what I asked earlier. Are there any open source formal tools that we can use with System Verilog, for example?
Most formal tools are open source. In fact, I will go even farther. It would be harder for you to figure out which one to use. There are SAT conferences and there are SAT competitions. Every year, whoever was, when I was doing PhD, the Princeton tool was GCHAF. I still use it today because of fascination and because I learned in childhood. But every year, whichever is the best SAT solver, somebody else is beating it, and all of them are public domain. But as of today, if you are thinking of a name, if you say, okay, give me a name. So EBMC is probably robust, and it comes with a lot of support. It can connect with Berkeley ABC tool and many other tool. So this is a bounded model checker tool. And in terms of theorem provers, there are so many. So there are COQ, there are Hall. It based on all of their own languages, depending on which university it started, how it started. There are many. There are many theorem prover. There are many model checker. And if you want to just start with one of them, this one you can start with. And there are too many SAT solvers. Some of them are SAT solver for kind of for linear time logic, some of them for temporal logic. So each of them is kind of, some of them are specifically for software, some of them are specifically for hardware, some of them can do transaction level, RTL. So each of them has pros and cons, but there are too many of them. And most people use or at least the kind of research we do in most of our papers, you will see this name. It's an ISIS SMT solver, EBMC model checker, and then concolic testing tool. So there are few tools which most people use, but as I said, there are many more. It would be incorrect for me to say, okay, just this and that, ISIS and nobody else. There are many open source tools. In formal verification domain, actually, there are too many. And they not only come with tutorial, they also come with benchmarks and what you can run and all that stuff. And
That's
some of
great.
them are
Thank you.
very robust. These are very robust. But some others are going to work mostly on the benchmarks they put in. Anything else you run, there are no guarantees.
Yeah, and you mentioned also that there are tools that can convert specifications to the input that these tools understand.
Yes. You go to those tool site, they will tell you which tool, like Ikara's Verilog simulator, for example, that you need to run. They have a methodology. They'll tell you what to install, what to do. They will exactly walk you through. So you exactly know, you don't have to convert manually your Verilog code to your conjunctive normal form, for example. Either the tool already have everything integrated if you compile it correctly, or you do different components separately and run them.
Thank you very much.
You're welcome. Any other questions? If you have no other questions, thank you very much. Have a wonderful time in ES week and rest of your day. Thank you. Bye.
Thank you, sir.
You are welcome. Bye, everyone.